The seal never sees the ocean disappear beneath it. One moment, sunlight fractures across the surface in blinding shards, turning the sea into a shifting mirror. The next, gravity vanishes. A pale torpedo detonates upward from darkness, jaws opening not in rage, but in calculation. The entire breach lasts less than a heartbeat, yet it is the final product of a geometry problem solved in motion. Distance measured in body lengths, angle measured against solar elevation, acceleration calibrated against the resistance of water itself. The predator is not simply fast, it is precise. And precision in this ecosystem is the difference between spectacle and starvation. Beneath the surface, the great white shark, Carcharodon carcharias, does not patrol randomly. It holds depth like a sniper choosing elevation, positioning itself in the dim corridor below a colony of Cape fur seals. This vertical staging area is not arbitrary. Light behaves unpredictably at the air-water boundary. The sun's angle fractures into glare, creating a luminous ceiling that blinds any creature looking downward from above. For the shark, this glare is a weapon. From below, prey silhouetted against that radiant sheet becomes a dark cutout, clearer, sharper, easier to track than against the cluttered reef. The surface that protects the seal from land predators becomes the backdrop that betrays it to the sea. But the shark cannot simply rush upward at every passing shadow. Water is dense, nearly 1,000 times denser than air, and acceleration is metabolically expensive. A full breach costs energy equivalent to multiple failed pursuits. Too many miscalculations and the shark risks metabolic deficit in a landscape where feeding opportunities are episodic, not constant. The shark must wait for the perfect vertical timing window, when a seal is directly overhead, when its trajectory aligns with a straight ascension path, and when the sun sits at an angle that maximizes silhouette while minimizing the seal's ability to see into the glare. If the shark launches too early, it generates a pressure wave detectable by the seal's whiskers and lateral line. Seals are not naive swimmers. Their vibrissae can sense minute hydrodynamic disturbances, allowing them to detect the wake of passing fish. A premature acceleration creates turbulence that ripples upward, translating into warning. The seal veers. The ambush fails. If the shark launches too late, the prey has already crossed the optimal intercept angle. Water resists abrupt directional change. A late strike becomes a chase, and chases favor the more maneuverable seal. So the shark waits in suspended calculation. Its ampullae of Lorenzini, sensitive electroreceptors embedded in the snout, scan for the faint bioelectric signatures of muscle contraction above. Its eyes, equipped with a reflective layer known as the tapetum lucidum, amplify minimal light. Its brain, though smaller proportionally than that of many mammals, is highly developed in regions governing sensory integration. The shark is not thinking in abstraction. It is processing vectors. Distance collapses into instinctive mathematics. Then the moment arrives. The seal crosses overhead with the sun behind it. The glare blinds downward vision, converting the seal into a black silhouette against brilliance. The shark's body arches. Its caudal fin sweeps in powerful oscillations, converting stored elastic energy in white muscle fibers into explosive thrust. Acceleration spikes. In less than 2 seconds, the shark crosses vertical distance that would exhaust most marine predators. The ocean compresses around it. Cavitation trails behind its snout. At the surface, the geometry resolves. The shark's jaws strike upward, targeting the midline to induce catastrophic trauma. Impact may launch both predator and prey skyward in a breach that seems theatrical, but is in fact collateral physics. Momentum meeting a boundary. Air offers no resistance compared to water. The shark's upward velocity converts into vertical lift. But this airborne display is not the objective. The objective was calculated milliseconds earlier, when light, angle, and silhouette aligned. Here is the twist that reshapes the spectacle. The breach is not about strength. It is about invisibility engineered by light. The shark does not dominate the seal through brute force alone. It manipulates the physics of the surface. The glare that humans find beautiful, sparkling sunlight on waves, is, in ecological terms, a sensory blindfold. The shark turns the ocean's reflective properties into camouflage, ascending from a zone where it remains nearly undetectable until kinetic inevitability takes over. Yet this perfection is fragile. Vertical timing depends on solar elevation, which shifts with season and latitude. During overcast conditions, glare diminishes, silhouettes blur, and the shark's advantage narrows. In turbid water, suspended particles scatter light, reducing contrast and compressing the effective ambush corridor. The predator must adjust depth, approach angle, even hunting time. What appears to be a universal killing machine is in fact exquisitely dependent on environmental optics. The seal colony, meanwhile, evolves countermeasures. Seals launch from haul-out rocks in chaotic bursts, creating unpredictable trajectories that disrupt the shark's intercept calculations. They swim in tight groups, increasing the complexity of silhouette interpretation. A cluster of overlapping bodies confuses the single-target geometry required for a precise breach. The shark's sensory systems are powerful, but they are tuned for clarity, not clutter. Confusion reduces success probability. And so the predator becomes, in subtle ways, constrained by its own specialization. The great white's body is built for speed in straight lines. Its torpedo shape minimizes drag, but sacrifices agility. In horizontal chases through kelp forests or reef labyrinths, the seal often outmaneuvers the larger hunter. The vertical strike compensates for this limitation. It is not merely an attack style. It is a biomechanical solution to a structural weakness. What appears to be dominance is actually adaptation to constraint. Beneath this choreography lies thermodynamics. The great white is regionally endothermic, capable of maintaining muscle temperatures above ambient water through countercurrent heat exchange systems known as retia mirabilia. Warmer muscles contract more powerfully, enabling the explosive acceleration required for vertical ambush. But heat retention demands caloric intake. Each failed breach burns precious reserves. The shark's metabolism imposes discipline. It cannot afford recklessness. There are days when the shark aborts mid-ascent. Electroreceptors detect an angle shift. The seal alters course by a fraction of a degree. The shark senses the misalignment and decelerates before breaking the surface, conserving energy for a better window. From above, nothing appears to happen. From below, a lethal equation was solved and discarded in less than a second. Occasionally, the calculation fails spectacularly. The shark breaches into empty air, jaws snapping shut on nothing but glare. The seal darts aside, propelled by reactive muscle fibers adapted for burst escape. The predator crashes back into water, momentum dissipating into foam. In that instant, the seal is not prey, but victor. The ecological hierarchy reverses. The shark, apex though it is, becomes temporarily inefficient, exposed, energy depleted. This reversal underscores a deeper truth. The great white's power is contingent. It depends on the intersection of celestial mechanics, fluid dynamics, sensory biology, and split-second decision-making. Remove one variable, alter light angle, increase turbidity, disrupt seal behavior, and the advantage shifts. Apex status is not permanent dominance, but optimal performance within a narrow window of conditions. When the timing aligns perfectly, the result appears effortless. The shark ascends, breaches, submerges with prey secured. Blood diffuses into the water column, signaling a brief feast before scavengers converge. But what the surface reveals is only the final frame of a longer sequence. Minutes of stillness, seconds of acceleration, milliseconds of decision. The ocean, vast and seemingly chaotic, here becomes a theater of vertical precision. Light, often treated as background illumination, is recast as active participant. The seal's world is divided into glare above and darkness below. The shark exploits that division. The attack is not random violence, but the culmination of a visual paradox. The brighter the surface, the deeper the blind spot. As the sun lowers toward the horizon, angles shift again. Shadows lengthen. The silhouette effect softens. The shark descends deeper, recalibrating its position relative to the new geometry of light. Hunting continues, but differently. The vertical timing window narrows with dusk, then vanishes. Night brings alternative strategies, slower pursuits, reliance on electroreception rather than silhouette. The breach, then, is a moment born of alignment. Distance, angle, and light must converge. The great white does not merely attack upward. It waits for the sun to participate. It calculates a moving ceiling of glare and commits only when the equation resolves in its favor. In that brief eruption from darkness, we witness not just predation, but the integration of physics and flesh. A reminder that in the open ocean, survival hinges not only on power, but on the exact instant when geometry turns lethal. The water does not ripple. The sand does not shift. A small reef fish drifts forward, hypnotized by what appears to be a trembling worm suspended in the current. There is no visible predator, no tightening coil of muscle, no warning flare of motion. Then the water itself implodes. In less time than it takes a nerve impulse to travel from a human fingertip to the brain, the drifting fish vanishes. There is no chase, no splash, only a sudden vacuum and the faint pulse of displaced sand. The frogfish has already swallowed. The strike lasts a fraction of a blink, but its precision is built on patience measured in hours. A frogfish does not hunt by pursuit. It hunts by geometry. Its entire predatory system is governed by a narrow, invisible boundary in front of its mouth, a three-dimensional capture zone defined not by vision alone, but by fluid dynamics. Within this zone, suction becomes inevitable. Outside it, even by a few millimeters, the attack fails. The frogfish's success depends on waiting until prey crosses exactly into that window of hydrodynamic dominance. Unlike streamlined hunters that rely on speed, frogfish are architectural predators. Their bodies are globular and irregular, covered in dermal appendages that mimic algae, sponge filaments, or encrusting coral. Pigmentation shifts over weeks to match the surrounding substrate, a form of morphological plasticity that aligns with reef succession and seasonal algal growth. They do not blend into the reef. They become part of its textural grammar. To passing prey, they are not threat but terrain. The deception extends to the lure. Modified from the dorsal spine, the elysium arcs forward, ending in a fleshy esker that pulses with subtle motion. The movement is not random. It imitates the erratic tremor of small crustaceans or worms displaced by current. Neurological studies suggest that frogfish can modulate lure rhythm depending on prey behavior, adjusting amplitude and frequency to mimic specific stimuli. The lure does not simply attract. It calibrates expectation in the prey's visual system, drawing it forward through conditioned curiosity. Yet the lure alone cannot guarantee capture. The frogfish's mouth is not a snapping trap. It is a vacuum generator. When the prey crosses into the strike radius, the frogfish's buccal cavity expands with explosive speed. Muscles attached to the hyoid apparatus contract, depressing the floor of the mouth and creating a rapid pressure drop. The surrounding water accelerates inward, carrying the prey with it. The entire suction event occurs in approximately 6/1000ths of a second, making it among the fastest feeding movements recorded in vertebrates. But this speed is only effective within a narrow spatial envelope. Suction feeding relies on pressure differentials that dissipate rapidly with distance. If the prey hovers just beyond the optimal range, the inward flow weakens, and the prey may be jostled but not captured. If the frogfish strikes too early, when the prey is still approaching, it wastes energy and reveals itself, teaching the reef's small inhabitants to avoid that patch of coral. If it waits too long, the prey's own escape reflexes, triggered by minute shifts in water movement, activate, and the fish darts away in a burst, powered by fast-twitch white muscle fibers. The frogfish must therefore solve a temporal puzzle. Its eyes, positioned high on its head, provide depth cues in a world of refracted light. Its lateral line detects vibrations from approaching bodies. Neural circuits integrate these inputs in real time, assessing velocity, trajectory, and proximity. The strike is not a reflex in isolation. It is the endpoint of microsecond-level computation. When the prey's forward momentum carries it into the suction envelope, the frogfish triggers the expansion. Too early or too late, and the reef remains hungry. There is an additional constraint. The frogfish's body design limits repositioning. Unlike agile predators that can correct mid-lunge, frogfish are sedentary. Their pectoral fins resemble limb-like structures that allow crawling across the substrate, but rapid pursuit is impossible. This immobility forces reliance on exact timing rather than corrective speed. The frogfish cannot chase a missed meal. It must let the ocean bring the next opportunity. The strike's invisibility is not merely a product of speed, but of concealment within ambient flow. Coral reefs are dynamic systems, with constant microcurrents generated by tides and wave action. These flows mask the initial pressure changes created by the frogfish's buccal expansion. Prey species have evolved startle responses triggered by hydrodynamic cues, yet the frogfish's suction is so localized and rapid that by the time the disturbance registers, the prey is already inside the mouth. The predator exploits the temporal lag in sensory processing, a biological blind spot measured in milliseconds. The apparent stillness before the strike is itself a metabolic strategy. Remaining motionless reduces energy expenditure in an environment where caloric gain is unpredictable. Reef productivity fluctuates with plankton blooms and predator presence. The frogfish's sit-and-wait approach aligns with these fluctuations, minimizing metabolic cost while maximizing capture efficiency during prey abundance. In ecological terms, it occupies a niche of low-movement, high-precision predation. Yet here the narrative reverses. The frogfish's greatest strength, its reliance on proximity, also makes it vulnerable. Larger predators, including groupers and moray eels, detect the frogfish not as camouflage, but as anomaly. Chemical cues emitted by stressed frogfish tissue betray their presence. If discovered, the frogfish cannot outrun pursuit. Instead, it relies on cryptic stillness and, in some species, the ability to inflate slightly, increasing apparent size and making ingestion more difficult. What appears to be a supreme ambush specialist is, in the broader reef hierarchy, a mid-level predator walking a narrow line between feast and fatality. Even its strike mechanism imposes trade-offs. The rapid expansion of the buccal cavity requires precise muscle coordination and structural reinforcement of the skull. These adaptations prioritize suction over bite force. Frogfish do not crush prey. They engulf it whole. This limits the size range of viable targets and forces the predator to calibrate its lure to species small enough to swallow. Precision in timing must be matched by precision in prey selection. At night, the reef's sensory landscape shifts. Visual cues diminish, and many prey species rely more heavily on lateral line detection. The frogfish's success rate may decrease if hydrodynamic noise is reduced, making suction disturbances more perceptible. In such conditions, patience extends even further. The predator must wait for the rare moment when current turbulence masks the impending strike. The most astonishing element remains the scale of the timing window. Research suggests that effective suction range may be measured in only a few centimeters, a capture zone so small that it demands almost surgical precision. Within that envelope, water acceleration is unstoppable. Outside it, the same predator is inert sculpture. The frogfish's world is divided into lethal centimeters and harmless distance. This razor-thin margin reshapes our understanding of predation. Speed alone does not define mastery. Precision does. The frogfish embodies an evolutionary solution that compresses decision-making into microseconds and space into inches. It does not overpower the reef. It waits for the reef to align. As the drifting fish disappears into the expanding mouth, sand settles almost immediately. The lure resumes its tremor, indistinguishable from before. There is no celebration, no visible exertion. The frogfish has consumed not only prey but the evidence of action. The ocean closes around the event, erasing disturbance as if nothing occurred. In that silence lies the true marvel. The frogfish's strike is not dramatic in spectacle but in exactness. It is a predatory system tuned to a vanishingly small window of space and time, where fluid mechanics, neural processing, and behavioral patience converge. Too early and the vacuum collapses without reward. Too late and opportunity dissolves into current. But at the precise instant when prey crosses into the invisible boundary, the reef itself seems to fold inward, and life is absorbed in a blink measured in thousandths of a second. What remains is a still figure on the coral, indistinguishable from sponge and shadow, waiting once more for geometry to resolve into inevitability. The ice edge shudders before it breaks. A seal sprawls across the floe, its whiskers twitching in the brittle polar wind, unaware that beneath the frozen ceiling, a black and white formation is adjusting depth by centimeters. There is no rush, no scattered pursuit. The orcas hold position in silence, each body angled with geometric intention, each fluke suspended in cold water that steals heat faster than air ever could. Then, without visible signal, they surge. A rolling wall rises against the ice shelf, water piling where water should not climb. The floe tilts. The seal slides. The ocean claims it in a heartbeat. The wave did not happen by chance. It was calculated in synchrony. Orcas, Orcinus orca, are not solitary assassins. They are architects of collective timing. When they hunt seals on ice, the success of the maneuver depends not on raw power, but on hydrodynamic choreography. Each individual must match acceleration, angle, and force so that their combined thrust produces a single, unified surge. If one animal accelerates too early, the wave fragments. If another lags, the crest loses height. The seal remains dry and alive. Coordination is not decorative. It is structural. Beneath the floe, the pod aligns in a staggered row, bodies parallel, spacing calibrated to prevent turbulent interference between flukes. Hydrodynamics dictates that water displaced by one animal alters the flow field experienced by the next. To generate a coherent wave, they must synchronize tail beats within fractions of a second, converting individual momentum into cumulative displacement. The ocean, dense and resistant, becomes a tool only when forces are additive rather than chaotic. The strike begins with a shared inhalation at the surface, lungs replenished with oxygen for the anaerobic burst ahead. Orcas possess high myoglobin concentrations in their muscles, allowing prolonged dives without immediate fatigue. This physiological adaptation underwrites their strategic patience. They descend together, then accelerate upward at a shallow angle toward the ice edge. Flukes beat in rhythm, driving water forward and upward. The surge hits the floe not as scattered splashes, but as a coherent force. Above, the seal's sensory world betrays it. On ice, its evolutionary advantages dominate. In water, it is agile. But in this liminal zone, where ice meets sea, its escape routes narrow. The wave undermines the flow's stability, tilting it just enough to negate friction. The seal slides, momentum carrying it into open water where the orcas wait. The reversal is immediate. The ice that promised safety becomes a ramp into danger. Yet even this iconic strategy hinges on precision beyond spectacle. The size of the flow matters. Too large, and the generated wave dissipates before achieving lift. Too small, and the flow may flip unpredictably, creating chaos that benefits prey. The orcas must assess ice thickness, seal position, and water depth. Juveniles observe, learning the physics of wave amplitude through repetition and error. Cultural transmission, not instinct alone, refines the technique. Pods in different regions exhibit distinct hunting traditions, evidence that timing is socially inherited knowledge. The complexity deepens when the prey is not solitary but collective. In temperate waters, orcas target schooling fish, such as herring, whose defense lies in synchronized movement. A school operates as a living algorithm, each fish adjusting position based on neighbor proximity, creating a fluid, evasive mass. To penetrate this defense, orcas deploy a counter-algorithm. They encircle the school, releasing bursts of bubbles that rise in shimmering curtains. The bubbles are not random. They form a cylindrical barrier that compresses the fish into a tight ball, a phenomenon known as herding. Compression increases prey density, but also elevates collective vigilance. A premature strike scatters the school, dissolving the opportunity. Orcas therefore take turns lunging through the mass, stunning fish with powerful tail slaps. Each slap must be timed so that the school remains cohesive, yet disoriented. Too many simultaneous lunges fragment the formation. Too few allow escape corridors to open. The pod operates as a distributed intelligence, adjusting spacing and timing in real time. The neurological substrate for this coordination lies in advanced social cognition. Orcas possess large brains relative to body size, with expanded cortical regions associated with communication and learning. Vocalizations function not merely as contact calls, but as tactical signals, modulating group movement beneath the surface where vision may be limited. Echolocation clicks provide spatial mapping, while subtle shifts in body posture cue acceleration. Communication is continuous, though often beyond human auditory range. Timing is therefore shared, not centralized. No single orca commands the strike. Instead, feedback loops between individuals create emergent synchrony. Studies of cooperative predators suggest that such coordination minimizes energetic waste. By distributing effort across the pod, each member reduces the metabolic burden of pursuit. In cold waters where thermoregulation is costly, efficiency is survival. Yet the narrative reverses when the environment resists. In rough seas, wave formation becomes unpredictable, diminishing the effectiveness of seal washing strategies. Ice flows fracture irregularly, creating unstable platforms that thwart coordinated surges. If even one orca misjudges the angle of approach, the wave dissipates sideways. The seal remains perched. Energy expended yields nothing. The pod must regroup, recalibrate, and attempt again. Similarly, in fish hunts, a single mistimed lunge can scatter the school irreversibly. Herring react to hydrodynamic shock waves. If the pressure disturbance exceeds a threshold, the ball explodes outward. Orcas then face the metabolic cost of re-herding, a process that may require extended chases. The failure of one individual reverberates across the group. Collective timing is fragile. This fragility underscores a deeper truth. The orca's power is inseparable from social cohesion. Solitary individuals lack the capacity to generate ice-breaking waves or to contain vast schools. Isolation reduces them to opportunistic hunters rather than strategic engineers. The apex predator status attributed to orcas emerges not from individual dominance but from synchronized behavior. The sea itself imposes constraints. Sound travels efficiently in water, enabling long-distance communication, yet temperature gradients and salinity layers can refract acoustic signals. Pods must adapt to shifting soundscapes, adjusting vocal amplitude and frequency. Coordination depends on reliable transmission. Environmental noise, from storms or anthropogenic sources, can disrupt the subtle cues that maintain synchrony. And still, when conditions align, the effect is astonishing. A seal slides from ice into a waiting mouth. A sphere of fish collapses under orchestrated strikes. The success appears seamless, as though choreographed by a single mind. But beneath the surface, each movement is contingent on shared timing windows measured in seconds and sub-seconds. There is another reversal embedded within this spectacle. The seal, though often victim, is not passive. On smaller flows, seals position themselves near the center, increasing the energy required to tilt the ice. They may cluster on irregularly shaped platforms that absorb wave force. Fish schools adjust density dynamically, tightening when predators approach to increase the confusion effect. Prey strategies evolve in response to coordinated predation, shaping a feedback loop of tactical escalation. Thus, the orca pod's synchronized strike becomes part of a broader ecological dialogue. Success influences prey behavior, which in turn reshapes future hunts. Cultural knowledge within pods adapts across generations, refining timing as prey tactics shift. What we witness is not static mastery, but evolutionary negotiation. As the ice settles and the water stills, the pod regroups. Calves surface beside adults, absorbing not only oxygen, but experience. Timing is learned through immersion, through the feel of fluke beats aligning with others, through the subtle delay between acceleration and wave crest. The ocean teaches through repetition. In the polar light, the black dorsal fins cut through grey water like metronomes marking tempo. Each hunt reinforces a truth that transcends individual prowess. In this ecosystem, survival belongs to those who can synchronize. The orca's greatest weapon is not tooth or speed, but shared precision. The capacity for multiple bodies to act as a single hydrodynamic force. When the next flow drifts into range, the formation tightens once more. The pod sinks beneath the surface, timing breaths and depth as if rehearsing an invisible score. The seal above remains unaware that below, a calculus of cooperation is unfolding. And when the surge comes, it will not be the impulse of one predator, but the collective pulse of many converging in perfect alignment, turning water into weapon and unity into inevitability. The crab freezes for a fraction of a second that should not exist. Its antennae are extended, sensory hairs sampling the water for pressure changes, compound eyes tuned to motion that would normally trigger instantaneous escape. In the language of reflex, hesitation is lethal, and yet it hesitates. Across from it, the cuttlefish has not lunged, not accelerated, not revealed the violence coiled within its mantle. Instead, bands of light ripple across its skin in a slow, hypnotic cascade, dark to pale, pale to iridescent green, each pulse arriving at precisely the wrong speed for the crab's nervous system to categorize as threat. The crab's reflex arc falters. In that microscopic gap, the cuttlefish strikes. The strike itself is mechanical perfection. Two feeding tentacles, normally hidden within the arms, launch forward with elastic recoil generated by specialized muscle fibers that store potential energy before release. The extension is blisteringly fast, measured in thousandths of a second, and the club tips adhere to the prey with suction cups armed with minute teeth-like structures. But the speed of extension is not the most remarkable element of the hunt. The marvel lies in what preceded it. The deliberate manipulation of the prey's reaction timing. Cuttlefish are masters of neural deception. Their skin is layered with chromatophores, pigment containing cells controlled directly by motor neurons, allowing color changes that occur faster than most vertebrate muscle contractions. Beneath these lie iridophores and leucophores, structures that reflect and scatter light to create shimmer, polarization shifts, and dynamic contrast. The animal can alter not only hue, but brightness and pattern orientation in less than a heartbeat. These visual displays are often interpreted as camouflage, but during hunting, they become cognitive weapons. Prey animals rely on hardwired escape responses triggered by specific visual thresholds. A looming object of increasing size, a sudden high-contrast edge, or a rapid directional movement activates neural circuits that bypass conscious processing. Reaction time becomes automatic. The cuttlefish disrupts this system not by exceeding the threshold, but by dancing around it. The flashing patterns create rhythmic oscillations in brightness that resemble environmental noise, flickers of sunlight refracted by waves, or drifting shadows of algae. The crab's visual neurons register change, but do not categorize it as immediate danger. This is where the timing becomes psychological. The cuttlefish's patterns are not random bursts of color. They are calibrated sequences that exploit the prey's decision-making delay. Neuroscientists describe this delay as the time required for sensory input to accumulate enough evidence to trigger action. By presenting ambiguous stimuli, neither clearly threatening nor entirely benign, the cuttlefish extends this evidence-gathering window. The crab waits for confirmation that never arrives. Its motor neurons hover on the brink of firing, suspended between escape and indifference. While the prey's nervous system stalls, the predator advances imperceptibly. Cuttlefish locomotion during stalking is subtle, driven by fine undulations along the mantle that produce minimal hydrodynamic disturbance. The lateral line systems of crustaceans detect water movement, but the cuttlefish approaches within that sensory blind zone where current-induced noise masks its presence. The flashing intensifies slightly, drawing the prey's visual focus forward. Attention becomes tunneled toward pattern rather than position. Then, precisely when the prey's hesitation peaks, when its neural circuits have been flooded with ambiguous signals and are momentarily overloaded, the tentacles fire. The extension is not only fast, but strategically delayed. If launched too early, before the prey's reaction threshold is softened, the crab would leap backward in a burst of muscular contraction. If launched too late, The prey might reclassify the flickering as abnormal and initiate escape. The cuttlefish chooses the instant of maximal indecision. This manipulation of reaction timing represents a rare form of predatory strategy. Cognitive interference. Rather than overpowering the prey's senses, the cuttlefish exploits the architecture of those senses. Visual neurons in crustaceans are tuned to detect looming threats. Gradual or oscillating changes may be filtered as background motion. By matching the frequency of environmental flicker, sunlight filtering through kelp fronds or sand ripples, the cuttlefish embeds itself within the prey's perceptual noise. The predator does not hide. It reframes itself as irrelevant until the final instant. The dual-layer brilliance lies in the cuttlefish's own neural sophistication. Cephalopods possess some of the most complex brains among invertebrates, with large optic lobes dedicated to visual processing. Their motor control of chromatophores is direct, bypassing hormonal delays that limit color change in other animals. This architecture enables split-second modulation of pattern intensity and orientation. The animal can switch from cryptic mimicry to high-contrast display in less than a blink, adjusting its visual signal mid-hunt based on prey response. Yet this extraordinary control carries metabolic cost. Rapid neural firing and chromatophore activation demand energy. The cuttlefish must balance the energetic expense of display against the caloric gain of prey. Overuse of flashing patterns may alert other predators, including fish that recognize cephalopod signals as hunting behavior. Thus, the timing of visual manipulation must align not only with prey hesitation, but with environmental safety. The narrative shifts again when we consider that the cuttlefish itself is prey. Larger fish, dolphins and sharks hunt these cephalopods, forcing them into a life of constant vigilance. Their flashing patterns, so effective against crabs and shrimp, can also betray them if misused. To survive, they must regulate the amplitude and frequency of displays, ensuring that their psychological warfare remains targeted and discreet. The same neural machinery that confuses prey can, if mistimed, attract danger. There is a deeper ecological implication in this dance of hesitation. On reefs and seagrass beds where visual clutter is abundant, animals that can manipulate perception gain advantage without escalating into energy-intensive chases. The cuttlefish's strategy exemplifies an evolutionary arms race, not of speed, but of interpretation. Prey species may evolve quicker decision thresholds, reducing hesitation at the cost of false alarms. Such hypersensitivity drains energy and increases stress, influencing feeding patterns and growth rates. Thus, a microsecond of manipulated indecision can ripple outward into trophic dynamics. Consider the strike from the crab's perspective. Its survival depends on discriminating harmless environmental flicker from predator approach. Too sensitive, and it wastes precious energy fleeing shadows. Too tolerant, and it risks death. The cuttlefish occupies the narrow band between these extremes, presenting stimuli that exploit the prey's compromise. The hesitation is not stupidity. It is the unavoidable byproduct of balancing caution with efficiency. The predator leverages that balance. Even the mechanics of the tentacle launch reveal timing finesse. The tentacles are stored in coils within the arms, tensioned before release. When fired, they extend and retract with astonishing speed, minimizing exposure. The window during which the cuttlefish is vulnerable, arms extended, body committed, is brief. If the prey escapes during that extension, the predator's balance may falter, leaving it exposed to nearby hunters. Precision protects both predator and strategy. As the captured crab is drawn inward, the cuttlefish's beak delivers a crushing bite, injecting saliva containing enzymes that begin pre-digestion. The chromatophores dim. The flashing ceases. The environment returns to its ambient shimmer. The prey's hesitation has been converted into sustenance. Yet the story does not end with triumph. Juvenile cuttlefish must learn to modulate these patterns effectively. Early hunts may involve mistimed displays that trigger premature escape or attract unwanted attention. Through experience, neural circuits refine the sequencing of color pulses. Cultural transmission in cephalopods is limited compared to mammals, but individual learning shapes hunting proficiency. The most successful hunters are those who master not only speed, but psychological tempo. In the shifting light of coastal shallows, the cuttlefish resumes its slow drift. To an untrained eye, it appears as a fragment of coral come alive. Beneath its skin, however, lies a symphony of neurons and pigments ready to orchestrate the next hesitation. The ocean is filled with predators that chase, overpower, and pursue. The cuttlefish belongs to a rarer category, those that sculpt the moment before action, stretching time itself just enough to slip between decision and escape. In that infinitesimal pause, the gap between stimulus and response, the predator thrives. The crab's hesitation is not an accident, but an engineered delay, a neurological stall induced by flicker and ambiguity. And when the tentacles shoot forward, the strike feels inevitable, as though the outcome was decided long before motion began. In truth, it was decided in that fragile slice of suspended thought, where perception faltered and timing became destiny. The reef tightens into a silver knot and then, for the briefest fraction of perception, loosens. A single sardine drifts half a body length out of alignment, its attention diverted by the shimmer of its own neighbors. That microscopic lapse is all the Barracuda needs. The water does not announce the strike, it fractures. A torpedo shape that had been indistinguishable from shadow becomes acceleration incarnate. By the time the school compresses again, one body is gone, cleaved cleanly from cohesion before any alarm signal can propagate through the collective. This is not a chase. It is reaction time theft. The great Barracuda, Spherina barracuda, is built for linear violence. Its elongated body reduces drag, its forked tail converts muscle contraction into explosive thrust, and its jaws, armed with dagger-like teeth, are hinged for scissor precision rather than crushing force. But morphology alone does not secure prey in the open reef. Speed is meaningless if it collides with anticipation. Schooling fish survive by minimizing individual reaction lag. Each fish monitors the velocity and orientation of its neighbors, adjusting within milliseconds to maintain formation. The school functions as a distributed sensory organ, capable of detecting threats from multiple angles simultaneously. To penetrate this living shield, the Barracuda does something counterintuitive. It waits. Unlike predators that advertise presence through overt pursuit, the Barracuda adopts stillness as camouflage. It hovers at the edge of the school, body rigid, pectoral fins making imperceptible corrections to maintain position in the current. Its reflective scales mirror the glitter of the fish it stalks, exploiting the chaotic sparkle of reef light to dissolve its outline. In that stillness lies a neurological advantage. Prey animals tune their escape reflexes to motion. Looming shapes and rapid directional changes trigger neural cascades that fire motor neurons before conscious evaluation occurs. A motionless threat remains beneath the activation threshold. The school, sensing nothing urgent, resumes routine behavior, feeding, orienting, adjusting spacing. But routine contains vulnerability. No school is perfectly synchronized. Microgaps emerge as individuals reposition to optimize foraging or avoid collisions. These gaps are brief, often less than a heartbeat, but they create transient windows where the geometry of safety fails. The Barracuda's eyes, positioned forward for binocular overlap, detect these spatial anomalies with high acuity. It does not target the fastest fish. It targets the moment of deviation. Here lies the critical constraint. The attack must begin and end within a window smaller than the prey's reaction time. In many small teleost fish, visual reaction time to sudden stimuli may range from a few tens of milliseconds to slightly more under complex visual noise. If the Barracuda's acceleration exceeds that threshold, the prey cannot initiate escape before impact. If the strike lags even slightly, the fish's startle response, a powerful C-shaped flexion of the body, propels it away, and the opportunity dissolves. The Barracuda's musculature reflects this requirement. White muscle fibers dominate its mass, specialized for short anaerobic bursts rather than sustained endurance. These fibers contract rapidly, fueled by glycogen reserves that deplete quickly but deliver immediate power. The predator does not intend to chase for long distances. Its strategy is a single decisive surge calibrated to outrun perception itself. When the gap appears, a fish half a fin length outside formation, the barracuda's body coils almost imperceptibly. The initial acceleration is not gradual, it is ballistic. The surrounding water cavitates around its snout, pressure waves forming that might warn prey under slower circumstances. But because the strike begins from proximity and at maximal velocity, the hydrodynamic signal arrives simultaneously with the jaws. The prey's nervous system registers disturbance only as it is being seized. This is theft at the level of milliseconds. The barracuda does not merely move faster than the fish, it acts before the fish's neural circuitry completes its first calculation. In effect, it subtracts reaction time from the prey's survival equation. Yet the predator's reliance on this razor-thin window introduces fragility. If the school is tightly packed, with minimal spacing between individuals, the barracuda's jaws may collide with adjacent bodies, deflecting its trajectory and reducing efficiency. In such cases, the predator risks injury from scales or spines and expends energy without guaranteed capture. Too much cohesion in the prey becomes a defensive armor of numbers. Conversely, if the school fragments prematurely, perhaps due to another predator's intrusion, the barracuda loses the advantage of predictable geometry. Isolated fish are agile and capable of erratic escape paths. The barracuda's elongated body, optimized for straight-line acceleration, is less suited to tight maneuvering. The predator's strength becomes a constraint. The narrative reverses when we consider that stillness, the barracuda's chosen weapon, is also its vulnerability. Larger predators, reef sharks, groupers, even orcas in certain regions, detect barracudas as potential prey. A hovering silhouette may attract attention. The barracuda's reflective scales, while blending among schooling fish, can betray it against darker backgrounds. To remain still is to trust camouflage absolutely, a gamble that depends on environmental lighting and background complexity. There is also an ecological ripple beyond individual hunts. By selectively targeting fish that momentarily lose formation, barracudas exert pressure on schooling behavior itself. Schools that maintain tighter alignment reduce individual vulnerability, but increased cohesion can limit feeding efficiency by restricting access to plankton patches. Over evolutionary time, predators that exploit micro-deviations shape the balance between foraging freedom and defensive conformity in prey species. The barracuda's reaction time theft thus influences not only mortality, but behavioral architecture. Consider the sensory landscape from within the school. Each fish relies on its lateral line to detect pressure changes and on vision to monitor neighbors. The arrival of a predator's acceleration creates a wave of alarm that propagates through the group, but that propagation takes measurable time. The first fish struck has no chance. Those adjacent may respond in synchrony, bending away in a cascade of motion that resembles liquid metal recoiling. The barracuda anticipates this cascade and often angles its strike toward the leading edge of deviation, maximizing the probability that the reaction wave will carry additional prey toward its path. Yet precision must be absolute. If the barracuda misjudges distance by even a body length, the prey's escape reflex activates, and the school erupts into a sphere of chaotic motion known as a flash expansion. In that instant, the predator is engulfed in reflective confusion, its visual field flooded with glittering bodies. The opportunity collapses into entropy. Energy economics sharpen the stakes. Each burst drains anaerobic reserves, requiring recovery time during which the barracuda's metabolic rate spikes. In warm reef waters where oxygen solubility decreases with temperature, recovery may be slower, forcing longer intervals between attempts. Failed strikes accumulate cost rapidly. Precision is not aesthetic, it is necessary for survival. The most astonishing element remains the invisibility of intent. To an observer, the barracuda appears almost indifferent, suspended in the water column with an expressionless stare. But beneath that stillness, neural circuits are calculating vectors and timing thresholds. The predator waits not for hunger to intensify, but for geometry to align. It does not create chaos. It exploits the smallest fissure within order. As the school reforms after a strike, the gap closes, the silver bodies knitting back into collective shape. The barracuda drifts again, unhurried. The reef resumes its hum of grazing and flicker. But the lesson lingers within the school. Deviation is deadly. Reaction time theft is a strategy built on understanding the limitations of another organism's nervous system. It acknowledges that every escape response has latency. Every sensory pathway requires processing time. The Barracuda inserts itself into that latency, transforming microseconds into advantage. Speed in isolation is insufficient. It must intersect with the prey's blind interval, the instant before reflex becomes action. In that vanishingly small window, predator and prey exist in different temporal realities. For the fish, danger begins with perception. For the barracuda, success begins before perception even occurs. And so the reef becomes a theater not of brute force, but of temporal mastery, where survival hinges on who can act first within a span too brief to measure, yet vast enough to determine life or disappearance. The fish does not flee because nothing appears to approach. Its lateral line registers only the steady push of coastal current. Its eyes scan a column of clear tropical water fractured by sunlight, and its muscles pulse in routine foraging rhythm. Then the current shifts by a fraction, barely perceptible, almost indistinguishable from turbulence. The fish drifts forward into something that does not look like a predator. There is no lunge, no acceleration, no visible jaw. Instead, a lattice of nearly invisible filaments brushes its flank, and in that instant, the ocean itself becomes a weapon. The box jellyfish has already delivered a venomous barrage before the prey's nervous system finishes interpreting contact. This is not a hunt in the conventional sense. It is an ambush built into water flow itself. The box jellyfish, members of the class Cubozoa, are not passive drifters in the way many imagine. They possess complex eyes arranged in clusters, each equipped with lenses, corneas, and retinas capable of forming images. Yet during feeding, their strategy often hinges less on active pursuit and more on spatial positioning. Their tentacles, trailing from the corners of a cube-shaped bell, can extend several meters in some species, transforming the surrounding water into a three-dimensional minefield of microscopic harpoons known as nematocysts. Each nematocyst is a pressure-triggered capsule containing a coiled tubule tipped with venom. The discharge occurs in less than 1,000th of a second, driven by osmotic pressure that explosively averts the tubule into whatever has made contact. The mechanism is mechanical, not cognitive. Once triggered, it cannot be recalled. Therefore, success depends not on reflexive timing, but on being in the right place when prey movement intersects the tentacle curtain. Currents dictate everything. Coastal waters where box jellyfish thrive are dynamic systems influenced by tidal flux, wind-driven surface flow, and the thermal layering of shallow bays. The jellyfish adjust their vertical position within the water column, pulsing their bell to counteract drift and maintain orientation relative to light and substrate. They are not strong swimmers compared to fish, but they possess sufficient control to choose depth bands where prey density is highest. Juvenile fish and crustaceans often aggregate in zones where plankton concentrates, and those zones shift with changing current speed. The jellyfish's timing is therefore environmental rather than muscular. It waits not for the moment to strike, but for the moment when prey, carried by hydrodynamic pathways, enters the strike zone. The tentacles, extended and tensioned by the bell's rhythmic contractions, form a web that oscillates gently with water movement. Each oscillation increases the probability of contact while maintaining structural integrity. If currents are too strong, tentacles tangle and effectiveness decreases. If too weak, prey may navigate around them. In this interplay between predator and fluid, the box jellyfish becomes an instrument tuned to current velocity. Too far upstream and prey bypass the tentacles. Too deep and light gradients reduce prey activity. Too shallow and turbulence disrupts positioning. The jellyfish must calibrate its location to maximize collision probability without expending excessive energy. Here lies a paradox. The box jellyfish is often described as among the most venomous creatures in the sea, yet it does not chase its prey. Its lethality compensates for immobility. When contact occurs, venom rapidly disrupts ion channels in muscle and nerve cells, causing paralysis in small fish within seconds. The prey's swimming ceases, and cilia along the tentacles transport the immobilized body toward the bell. Timing of venom potency aligns with the passive strategy. Swift incapacitation prevents escape after accidental collision. But the ecological twist emerges when we consider vulnerability. The same tentacles that entangle prey can ensnare debris or attract predators resistant to venom. Certain sea turtles possess thickened skin and specialized mucus layers that reduce nematocyst penetration, allowing them to consume jellyfish with relative impunity. In these encounters, the passive predator becomes the meal, its reliance on environmental timing insufficient against a hunter adapted to its defenses. Moreover, the box jellyfish's positioning strategy exposes it to variability. Sudden shifts in wind direction can alter surface currents, displacing the jellyfish into zones with lower prey density or higher predation risk. Because the animal does not pursue prey actively over long distances, its feeding success fluctuates with environmental stability. In calm periods with predictable flow, prey drift reliably into tentacles. In turbulent conditions, timing collapses. There is an additional layer of sensory complexity. Unlike many sea cnidarians, box jellyfish have image-forming eyes capable of detecting vertical structures such as mangrove roots or shoreline shadows. Research suggests they use visual cues to avoid obstacles and maintain orientation within coastal habitats. This visual capability may also inform positioning relative to light shafts where prey silhouettes become more distinct. Thus, even passive timing is underpinned by active environmental assessment. The venom itself reflects evolutionary trade-offs. Producing potent toxins requires metabolic investment, and venom reserves are finite until replenished. Each nematocyst discharge expends a microscopic but cumulative cost. The jellyfish cannot afford to trigger indiscriminately. Its tentacles are sensitive to specific mechanical and chemical cues, reducing accidental discharge on non-prey surfaces. Passive timing is therefore refined by selectivity at the cellular level. The broader ecosystem feels the impact of this strategy. In regions where box jellyfish densities increase seasonally, juvenile fish mortality may rise, influencing recruitment patterns for reef species. Such pulses can cascade through food webs, altering predator-prey ratios and even affecting commercial fisheries. The timing of jellyfish blooms often correlates with water temperature shifts and nutrient influx, linking climate variability to predation pressure. Yet for all its lethal potential, the box jellyfish is governed by simplicity. It does not calculate trajectory or react to fleeting deviations as a barracuda does. Instead, it transforms water movement into inevitability. Prey behavior, darting unpredictably, weaving through plankton, intersects with tentacles that are themselves shaped by current. The predator's agency is diffused into environment. Imagine the coastal shallows at dusk. Small fish ascend to feed on plankton rising in the water column. The current slows as tidal exchange reaches equilibrium. In this transitional calm, tentacles hang almost motionless, forming vertical curtains. A juvenile fish, distracted by abundant prey, drifts into a filament it cannot see. Contact is instant. Venom injects. The fish's muscles seize, its escape aborted before it consciously registers threat. The jellyfish pulses gently, drawing sustenance inward. The narrative reversal lies in recognizing that the box jellyfish's greatest power is not aggression, but alignment. Its lethality depends on surrendering to flow rather than resisting it. What appears to be passivity is in fact a strategy of embedding within hydrodynamic patterns so thoroughly that prey movements become self-directed collisions. The jellyfish does not steal reaction time as a barracuda does, nor manipulate cognition like a cuttlefish. It lets the ocean deliver prey. This strategy also reveals vulnerability to human alteration. Coastal construction, pollution, and climate-driven shifts in current patterns can disrupt the delicate balance that governs jellyfish feeding success. Changes in predator abundance, such as overfishing of species that consume jellyfish, may allow populations to surge, intensifying their ecological footprint. Thus, passive timing intertwines with broader environmental dynamics. As night deepens and bioluminescent plankton flicker in the darkening water, the box jellyfish continues its slow pulsation. Its tentacles trace arcs that mirror the rhythm of tide. It does not chase, does not lunge, does not even appear to hunt. And yet every drift of water carries possibility. The timing is not counted in muscle contractions, but in currents and collisions, in the choreography of coastal physics. When prey and tentacle intersect, the event seems accidental. But within that accident lies design shaped by evolution. Positioning optimized for flow, venom calibrated for immediacy, sensory structures attuned to habitat contours. The box jellyfish turns passivity into precision, transforming environmental movement into lethal certainty. In its stillness, the ocean itself becomes the predator's accomplice, and timing is written not in reflex, but in tide. The crab pauses at the lip of its burrow, claws extended, antennae combing the water for vibrations. It believes it is alone. Behind a cluster of broken shells, an octopus has been watching for nearly 10 minutes, skin mottled to match the rubble, pupils narrowed into horizontal slits that sharpen contrast in shifting light. Nothing about the scene appears urgent, and that is precisely the point. The octopus does not strike when prey is present. It strikes when prey is exposed. Timing for an octopus is not measured in speed, but in decision. Unlike predators built for relentless pursuit, octopuses operate as analysts in an environment defined by complexity. Coral reefs and rocky seafloors offer labyrinths of crevices where prey can vanish within a blink. A premature lunge would send the crab backward into its hole, sealing the opportunity. A delayed attack risks the crab retreating on its own schedule. The octopus must identify not merely where the prey is, but when the prey's escape geometry is compromised. Its body is prepared for patience. The octopus has no rigid skeleton. Its musculature is organized as a hydrostat, allowing arms to bend, elongate, and compress with extraordinary flexibility. This softness permits it to mold itself into cavities and crevices, but it also demands strategic restraint. A sudden movement disturbs sediment and creates pressure waves detectable by sensitive crustacean receptors. The octopus waits until the environment itself provides cover, perhaps a passing surge of current or the shadow of a drifting cloud that shifts light contrast. The eyes of an octopus are highly developed, rivaling those of vertebrates in acuity. They can detect polarized light and subtle shifts in orientation. From its vantage point, the octopus monitors the crab's behavior not as isolated motion, but as pattern. Crabs alternate between vigilance and foraging, between guarded stance and exploratory extension. When the crab extends its claws outward to manipulate a fragment of algae, its defensive posture weakens. When it rotates slightly away from its burrow entrance, the direct path to safety elongates by a body length. These are not dramatic changes. They are fractional shifts in probability. Decision timing emerges from this observation. The octopus's nervous system is distributed. More than half of its neurons reside in the arms themselves, enabling semi-autonomous control. While the central brain evaluates visual input, the arms remain poised, capable of rapid extension. This distributed architecture allows the octopus to hold tension without overt movement, conserving energy until the moment of commitment. Too early, and the crab's escape reflex triggers. Crustaceans possess rapid neural circuits that initiate a backward dart powered by abdominal flexion. Once inside the burrow, the crab becomes inaccessible. Too late, and the crab may shift position, restoring optimal escape geometry. The octopus must strike within a narrow interval when the prey's body orientation, limb position, and distance from refuge align unfavorably. The strike itself is swift, but not reckless. An arm shoots forward, suction cups ready to adhere. Unlike suction-feeding predators that rely on vacuum, the octopus relies on grip and intelligence. Each sucker contains chemoreceptors capable of tasting the surface it contacts. The arm can adjust pressure and direction mid-extension, correcting for minor deviations. Yet the initial extension must occur before the crab's nervous system fully registers threat. This interplay between predator and prey is a contest of anticipation. The octopus's camouflage enhances its advantage. Chromatophores expand or contract to match substrate color and texture, while papillae on the skin alter surface relief to mimic rocks or coral. By reducing visual salience, the octopus extends the prey's reaction threshold. The crab perceives less immediate threat, delaying escape. There is a deeper neurological layer to this timing. Studies suggest octopuses engage in observational learning and problem-solving, indicating flexible cognition. During hunting, they appear to evaluate multiple options before acting. An octopus may reposition slightly to block a potential escape route before initiating the grab. This subtle adjustment, executed over minutes, reshapes the spatial dynamics of the encounter. The predator does not simply wait for vulnerability, it engineers it. The ecological twist lies in recognizing that this calculated patience is born of vulnerability. Octopuses are soft-bodied, lacking protective shells. They are prey for fish, sharks, and marine mammals. A failed attack that exposes them in open water can attract larger hunters. Therefore, the octopus's delay is not only about maximizing prey capture, but minimizing self-exposure. Decision timing balances hunger against risk. Consider a scenario in which the octopus observes a fish rather than a crab. Fish possess acute vision and lateral line sensitivity. An open water lunge would almost certainly fail. Instead, the octopus may extend a single arm slowly along the substrate, using minimal motion to avoid detection. It waits until the fish dips its head into a crevice to feed, temporarily reducing awareness of surroundings. In that moment, the octopus envelops the fish from behind, arms wrapping like a net. The prey's escape route, once multidirectional, narrows to nothing. The delay before attack is as critical as the attack itself. Each second of waiting accumulates information. The octopus assesses tidal movement, light angle, and prey rhythm. Its pupils constrict or dilate in response to illumination changes, sharpening visual contrast. It shifts chromatophore patterns subtly to maintain concealment as lighting shifts. All these micro-adjustments feed into the final decision. Energy economics reinforce this precision. Hunting consumes resources, and an octopus's lifespan is relatively short, often measured in a few years. Efficient feeding ensures reproductive success before senescence. Wasting energy on failed strikes reduces overall fitness. Thus, evolutionary pressure has refined not just speed, but judgment. There are moments when the octopus aborts entirely. The crab's posture never weakens sufficiently. The fish remains too far from cover. Rather than gamble, the octopus withdraws, blending seamlessly back into the reef. Patience replaces aggression. In these aborted hunts lies an invisible success, avoidance of unnecessary exposure. The reversal becomes stark when a larger predator enters the scene. A reef shark glides overhead, its presence shifting the hierarchy instantly. The octopus, once predator, becomes prey. Its arms retract, body compressing into crevices inaccessible to rigid skeletons. Camouflage shifts from hunting pattern to concealment pattern, mottled skin mimicking rock texture. The same decision timing that governed its attack now governs its survival. It waits for the shark to pass, delaying movement until danger recedes. In this fluid exchange of roles, timing proves universal. The octopus thrives not because it is fastest, but because it is selective. It strikes when escape probability for prey is lowest and predation risk for itself is minimal. It withdraws when those probabilities invert. As the crab ventures again from its burrow, unaware of the calculation unfolding nearby, the octopus's body remains motionless, eyes fixed. A wave passes overhead, dimming light momentarily. The crab pivots slightly away from safety to seize a drifting morsel. In that fractional rotation, the burrow entrance falls outside immediate reach. The octopus moves. The arm extends with lethal certainty, suction cups sealing against chitin. The crab's claws snap in reflex, but the delay between distraction and realization has been enough. Another arm follows, enveloping, guiding prey toward the beak hidden beneath the mantle. Venomous saliva begins to immobilize muscle tissue, ensuring compliance. The reef settles once more. Shell fragments drift. The octopus resumes camouflage, appetite briefly satisfied. The encounter lasted seconds. The decision that enabled it unfolded over minutes. In this realm of shadows and crevices, survival hinges on the choreography of hesitation and exposure. The octopus exemplifies a predator that hunts not by overwhelming force, but by reading behavior as if it were text, selecting the precise moment when the prey's narrative falters. Too early, and the story ends in escape. Too late, and the opportunity vanishes. But in that narrow interval when awareness dips and geometry shifts, the octopus acts with finality. Decision timing, then, becomes an art shaped by evolution, an interplay of perception, patience, and risk management. The octopus does not merely respond to the reef, it interprets it. And in that interpretation lies its power, the capacity to wait until the escape route is weakest, then transform stillness into inevitability. The chase has already lasted longer than it should. A mackerel breaks from the school in a burst of silver panic, muscles firing at maximum contraction frequency, tail beating in frantic oscillation that tears at the surrounding water. Behind it, the tuna does not lunge for a dramatic finish. It does not explode into a single decisive strike. It stays close. Close enough that the mackerel never regains rhythm, far enough that it cannot turn and counter. The predator's body slices through the blue with relentless, measured power, not sprinting toward a climax, but pacing toward a collapse that has already begun at the cellular level. This is not a hunt of seconds. It is a hunt of limits. Tuna, members of the tribe Thonini, are engineered for endurance in a way few fish are. Their bodies are tapered into near-perfect hydrodynamic forms, reducing drag coefficient through a combination of streamlined shape and retractable fins that fold into grooves to minimize turbulence. But the true marvel lies beneath the skin. Tuna are regionally endothermic. Through countercurrent heat, exchange systems known as retia mirabilia, they retain metabolic heat generated by red muscle activity, maintaining core temperatures above the surrounding water. Warmer muscles contract more efficiently, sustain power longer, and resist fatigue that would cripple cold-blooded competitors. The mackerel, by contrast, relies on bursts. Its white muscle fibers provide explosive acceleration, fueled anaerobically and depleted quickly. At the onset of the chase, it may outpace the tuna for a heartbeat or two, veering sharply, twisting into tight arcs that a larger predator might overshoot. But tuna do not overshoot. They modulate. The predator's tail beats at a steady frequency calibrated not for immediate capture, but for energy conservation. Its red muscle fibers, rich in mitochondria and supplied by high concentrations of hemoglobin in the blood, generate sustained aerobic power. Oxygen extraction efficiency allows prolonged pursuit without catastrophic lactic acid buildup. The tuna is not racing against the mackerel's speed. It is racing against the mackerel's stamina. As the chase unfolds, hydrodynamics becomes both weapon and environment. Water is dense, resisting acceleration with force proportional to velocity squared. Each burst by the mackerel incurs exponential energetic cost. The tuna, by maintaining consistent velocity, reduces oscillation in its own energy expenditure. It tracks the prey's trajectory with precision, minimizing wasted motion, its lateral line system detecting subtle pressure changes that reveal direction shifts even when visibility is compromised by plankton haze. The key to endurance timing is not persistence alone. It is assessment. The tuna reads the mackerel's fatigue through microsignals. Tail beats lose amplitude. Direction changes become less sharp. The body's angle relative to current shifts slightly off optimal hydrodynamic alignment. These are not dramatic signs. They are fractional degradations in efficiency that accumulate invisibly until they reach a threshold. Too early, and the tuna commits to a burst that allows the mackerel to re-engage escape reserves, triggering a final surge powered by remaining glycogen. Too late, and the mackerel may slip into a school or refuge where numbers and confusion reduce capture probability. The tuna must strike at the exact moment when the prey's muscular endurance falters, but before it regains environmental advantage. There is a metabolic clock ticking within both bodies. In the mackerel, oxygen debt accumulates as anaerobic pathways dominate. Hydrogen ions build within muscle tissue, interfering with contraction efficiency. Calcium cycling within muscle fibers slows. The fish's neuromuscular coordination begins to degrade subtly, not yet visible as weakness, but detectable as reduced burst amplitude. The tuna, insulated from such rapid fatigue by its aerobic specialization, maintains composure. The ocean around them is not static. Currents shear at varying depths, thermoclines create layers of differing density, and oxygen concentration fluctuates. Tuna exploit these gradients strategically. By guiding prey towards slightly warmer or lower oxygen zones, the predator increases metabolic stress. The mackerel, already taxed, finds its endurance window shrinking faster than expected. The environment becomes accomplice. The ecological twist emerges when we recognize that tuna are not merely individual hunters, but often part of loosely coordinated groups. In some scenarios, multiple tuna pursue a school, taking turns pushing prey into higher speed movement that accelerates fatigue. Each predator conserves energy, while another applies pressure. The collapse of prey becomes collective strategy. Yet even in solitary pursuits, the tuna embodies a similar principle. Distribute effort over time rather than concentrate it in a single strike. This endurance strategy influences prey behavior at ecosystem scale. Schooling fish must balance feeding time against predation risk from persistent hunters. In regions where tuna densities are high, prey may alter migration routes or vertical positioning to avoid prolonged chases. Such shifts ripple outward, affecting plankton consumption patterns and nutrient cycling. The reversal sharpens when a larger predator enters the equation. Sharks and billfish may target tuna themselves. The tuna's endurance, so advantageous against mackerel, becomes liability when faced with a predator capable of equal stamina and superior size. In such encounters, the tuna relies on speed bursts and tight maneuvers to evade capture. The same red muscle endurance that allowed relentless pursuit now fuels escape. Timing remains central, but the roles invert. Returning to the chase, the mackerel's movements begin to falter. Its tail beats shorten, its body alignment wavers. The tuna senses the impending failure, not as a dramatic collapse, but as a statistical inevitability. It accelerates slightly, not to maximum, but enough to close the narrowing gap. The final strike is efficient, jaws opening just as the prey's turn angle decreases below viable escape geometry. There is no explosive spectacle. The mackerel disappears into the predator's mouth with the inevitability of a clock reaching zero. Yet endurance timing carries inherent risk. Extended chases expose the tuna to increased visibility and potential competition. If the pursuit lasts too long, scavengers or rival predators may intervene, stealing the exhausted prey at the final moment. Energy spent without reward can be costly in open ocean systems where prey density fluctuates unpredictably. The tuna must judge not only prey fatigue, but environmental opportunity cost. Physiologically, the tuna's cardiovascular system underwrites this strategy. A large heart relative to body mass pumps oxygen-rich blood efficiently through muscle tissue. Elevated hemoglobin concentration enhances oxygen transport, sustaining red muscle contraction. Heat retention via countercurrent exchange ensures muscle enzymes operate at optimal temperatures even in cooler waters. These adaptations collectively allow the predator to outlast rather than outburst. The broader oceanic stage magnifies this dynamic. In pelagic zones where cover is scarce, escape options are limited to speed and direction change. Endurance predators exploit this openness. Prey cannot hide behind coral heads or retreat into burrows. The only defense is stamina. And against tuna, stamina often proves insufficient. As the tuna resumes steady swimming after the capture, its metabolic rate remains elevated briefly, then stabilizes. The ocean stretches endless and blue, currents weaving invisible highways. Somewhere ahead, another school flickers in the distance. The predator does not rush. It knows that victory does not belong to the swiftest sprint, but to the most patient pursuit. In this realm of open water, timing is measured not in milliseconds, but in minutes of sustained pressure. The tuna does not seize reaction gaps or manipulate perception. It shepherds prey toward exhaustion, calibrating effort to the point where collapse is certain, but not yet visible. The strike arrives at the threshold where movement slows just enough to be intercepted. Endurance timing reveals a different dimension of predation. It is not spectacle, but attrition, not ambush, but inevitability. The tuna embodies a strategy that transforms metabolic advantage into ecological dominance, pushing prey beyond their physiological ceiling and waiting, unhurried, for the precise instant when resistance turns into surrender. The head appears first, just a flicker of silver easing into shadow. A small reef fish slips toward a narrow crevice, drawn by the promise of shelter from open water predators. Its body angles downward, tail still outside, pectoral fins fanning as it commits to the corridor. Inside the darkness, something shifts, but not enough to trigger alarm. The fish advances one more body length. Now its turning radius is reduced. Its tail can no longer sweep freely. And in that compressed instant, when retreat and forward motion are equally constrained, the Moray erupts from the rock. The strike is not wide. It is surgical. Moray eels of the family Murayenidae are not hunters of open expanses. Their bodies are elongated and muscular, designed to thread through fissures that would halt rigid predators. Their scaleless skin secretes mucus that reduces friction and protects against abrasion within coral and volcanic rock. But the true theater of their predation lies in geometry. A crevice is not merely a hiding place. It is a funnel, a narrowing corridor that manipulates prey movement. Morays understand this architecture instinctively. From within a reef wall, the eel positions its head near the entrance of a tunnel, jaws slightly agape in a posture that appears almost perpetual. This open-mouthed stance is not aggression but respiration. Morays pump water across their gills by opening and closing their mouths, lacking the operculum that other fish use for ventilation. Yet this rhythmic gape also conceals readiness. The fish outside interprets it as background behavior, not imminent threat. The timing window begins the moment prey decides to enter the crevice. Reef fish frequently use narrow spaces as refuges from fast-moving predators like groupers or barracudas. These corridors offer safety only if the fish can maneuver freely. Once inside, the prey's escape options depend on distance from the entrance and the width of the passage. If the Moray lunges too early, when the fish's tail remains outside, the prey can reverse in a rapid burst and escape into open water. If the eel waits too long, the fish may pass fully through, emerging on the other side of the rock structure. The strike must occur when geometry collapses into inevitability. Morays possess a second set of jaws, known as pharyngeal jaws, mobile skeletal structures located in the throat. When the eel bites, these inner jaws shoot forward to grasp and pull prey inward, preventing escape even in tight confines. This adaptation allows Morays to secure struggling fish within crevices where suction feeding would fail. But the pharyngeal jaws are effective only if initial contact is achieved at the correct moment. The eel's sensory system contributes to this precision. Although their vision is relatively limited compared to pelagic predators, Morays rely heavily on olfaction. Their tubular nostrils extend forward, sampling chemical cues carried by water flow. The eel detects the scent of fish long before visual confirmation. It also senses minute vibrations through mechanoreceptors along its body, registering the approach of prey within the rock maze. As the fish inches inward, the eel remains motionless, blending into the reef's negative space. Its coloration, often mottled or banded, mirrors the encrusted rock. The fish perceives the crevice as static habitat, not occupied territory. Commitment deepens. The fish rotates slightly to align with the tunnel's axis, reducing its lateral escape vector. This is the moment the Moray has been waiting for. The strike unfolds in less than a second. The eel's body anchors against the rock, generating leverage as it snaps forward. Unlike open water predators that rely on forward propulsion, the Moray uses the rigidity of the crevice as counterforce. Its jaws clamp onto the prey's midsection. Immediately, the pharyngeal jaws engage, extending like a hidden arm to seize flesh and draw it backward. Escape routes vanish. Had the eel lunged a fraction earlier, the fish might have pivoted and fled. Had it hesitated, the fish might have reached a wider chamber beyond. But in this compressed corridor, the fish's turning radius is minimal. Its tail cannot generate sufficient thrust to overcome the eel's grip. Timing is everything. The ecological twist emerges when we recognize that the crevice itself is not inherently safe or dangerous. it is context-dependent. For the fish, it is refuge from larger predators. For the moray, it is an engineered trap. The same structural complexity that increases biodiversity in coral reefs also amplifies ambush potential. Reef architecture shapes predation strategies at a micro-habitat level. Morays are not solitary in influence. In some documented cases, they cooperate with groupers in a form of interspecific hunting. The grouper signals the moray to enter crevices where prey have hidden, flushing them back into open water. This partnership reveals a networked dynamic in reef predation. The moray's strength in tight spaces complements the grouper's power in open water. What appears as solitary ambush becomes part of a broader symbiotic choreography. Yet vulnerability shadows the moray's strategy. Anchored within a crevice, head exposed, the eel risks predation from larger hunters, such as reef sharks or even humans. Its elongated body, while flexible, cannot accelerate quickly in open water. If detected outside its structural advantage, the moray is less formidable. The crevice is both weapon and shield. Energy economics further refine timing. Morays do not pursue prey over long distances. Their hunting relies on opportunity intersecting with position. A missed strike expends energy and may alert nearby fish to the crevice's danger. Over time, repeated failures could render a particular hiding place unproductive as prey learn to avoid it. Thus, precision preserves both energy and anonymity. Within the narrow corridors of reef walls, hydrodynamics play subtle roles. Water flow through crevices is slower than in open water, creating pockets of reduced turbulence. Prey entering these zones may experience diminished sensory input from their lateral lines, reducing their awareness of subtle eel movements. The moray exploits this dampened signal environment, striking where detection probability is lowest. The reversal sharpens when the moray itself becomes prey. Large groupers or sharks capable of entering wider caves may target eels. In such encounters, the moray's elongated body allows rapid retreat deeper into labyrinthine tunnels, inaccessible to bulkier predators. Its apparent fragility in open water becomes resilience in complexity. The same anatomy that limits speed confers mastery of narrow domains. Back in the crevice, the eel consumes its catch, swallowing headfirst to streamline ingestion and avoid fin spines catching against the throat. The pharyngeal jaws retract, resetting for future hunts. Outside, small fish continue to dart among coral branches, unaware that within the reef's negative spaces, patience waits. Ambush timing in tight spaces is a study in commitment thresholds. The prey must cross a line of no return, a point at which retreat requires more energy than forward motion. The moray identifies that line not by conscious calculation, but through evolved instinct, sharpened by countless encounters. It strikes when the prey's geometry collapses into vulnerability. The reef itself becomes an accomplice. Cavities sculpted by centuries of coral growth and erosion create the corridors that define this strategy. Each crevice is a variable, width, length, curvature, shaping the optimal moment of attack. The moray's domain is not open water but architecture. In the end, what appears as a sudden eruption from darkness is in fact the culmination of stillness. Minutes of waiting condense into a single decisive snap, timed to the heartbeat of prey commitment. Too early, an opportunity evaporates. Too late, and the prey passes beyond reach. But at the exact instant when escape routes disappear, the moray transforms shelter into snare, revealing that in the reef's tightest spaces, survival is dictated not by speed, but by the precise moment when choice becomes impossible. The shell cracks before the eye can track the motion. A snail inches across coral rubble, antennae extended, unaware that a pair of compound eyes, each capable of independent rotation, have been calculating its distance for several seconds. There is no visible wind-up, no dramatic coil, only a blur, a shockwave, and the sudden fragmentation of calcium carbonate. The mantis shrimp withdraws its raptorial appendage almost as quickly as it extended it. The prey is stunned, its shell compromised not only by direct contact, but by a collapsing bubble that formed and imploded in the surrounding water. What appears to be brute violence is, in truth, precision timing measured against fractions of a body length. The mantis shrimp does not simply hit hard. It must hit at exactly the right instant. Mantis shrimps of the order Stomatopoda are divided broadly into smashers and spearers, each equipped with specialized appendages for different prey types. Smashers, the architects of shattered shells, wield club-like dactyls reinforced with complex microstructures that distribute impact stress and prevent self-damage. These appendages are powered by a latch and spring mechanism in which elastic energy is stored in saddle-shaped exoskeletal structures before being released explosively. The strike can reach accelerations comparable to projectiles fired from firearms, but such force is meaningless without exact spatial and temporal alignment. The shrimp's body length is small, its reach limited. Its prey, snails, crabs, bivalves, often remain in constant motion. If the mantis shrimp releases its appendage too early, the strike meets water instead of shell, expending stored energy without reward. The latch mechanism requires time to reset, and repeated misfires increase energetic cost and exposure to predators. If the strike comes too late, the prey may withdraw into its shell or slip behind cover, rendering the blow ineffective. The strike window is defined not only by distance, but by orientation. For maximum force transfer, the club must contact the shell at an angle that minimizes glancing deflection. An oblique hit dissipates energy along the surface, reducing fracturing potential and risking structural damage to the shrimp's own appendage. The mantis shrimp's compound eyes, among the most complex in the animal kingdom, play a critical role in this calibration. Each eye can perceive depth and motion independently, granting exceptional stereoscopic vision that refines distance judgment. These eyes do more than measure range. They detect polarization patterns and subtle shifts in reflectance that reveal shell thickness and microfractures. The shrimp may adjust aim slightly to target weaker structural points, exploiting the inherent brittleness of calcium carbonate under high strain rates. Thus, timing and placement converge. The appendage must be released when prey position, shell orientation, and limb alignment achieve optimal overlap. The mechanics of the strike amplify its significance. Upon release, the appendage accelerates so rapidly that it generates cavitation, a vapor bubble formed by localized pressure drop. When this bubble collapses milliseconds later, it produces a secondary shockwave capable of inflicting additional damage. For cavitation to enhance impact, the strike must occur at sufficient velocity and at close proximity. A mistimed strike that lands off-center may still create cavitation, but fail to channel its force effectively into the prey. Energy economics sharpen the stakes. The latch and spring system stores elastic potential through muscular contraction prior to release. Each charging cycle demands metabolic investment. Repeated strikes without successful capture drain reserves and increase vulnerability. Mantis shrimps inhabit burrows within reef substrates. Lingering outside for too long exposes them to fish predators. Therefore, the decision to strike is weighed against risk, and timing precision preserves both energy and safety. The ecological twist emerges when considering the mantis shrimp's own fragility. Despite their formidable weaponry, mantis shrimps are not apex predators. Larger fish prey upon them, and rival mantis shrimps engage in territorial battles that can result in limb loss. A miscalculated strike that damages the appendage compromises future survival. Evolution has therefore sculpted not only the appendage's strength, but also the neural circuitry governing its release. Precision protects the predator from itself. In territorial disputes, mantis shrimps often display rather than strike, raising their appendages in ritualized warning. The timing of actual blows in such contests is even more constrained. An early strike may escalate conflict unnecessarily. A late response may concede territory. The same impact timing precision that shatters shells governs social interaction. Returning to the hunt, the mantis shrimp waits at the entrance of its burrow, body partially concealed. Its eyes track a crab approaching cautiously. The crab's exoskeleton reflects polarized light differently at joints, revealing potential fracture points. The shrimp's appendage is already cocked, latch engaged. It inches forward slightly, minimizing the distance to target while maintaining stability. The crab pauses to probe the substrate. Its claws extend, momentarily exposing the carapace at a vulnerable angle. This is the instant the shrimp has been calculating. It releases. The appendage snaps forward in a motion too fast for human eyes to resolve. Contact is direct, perpendicular to the shell's curvature. The impact transmits force concentrated over a small area exceeding the tensile strength of the carapace. Simultaneously, cavitation forms and collapses, compounding structural damage. The crab recoils, stunned, its defenses breached. Had the strike landed milliseconds earlier, the crab's claw might have intercepted the blow. Had it been delayed, the crab could have retracted into a protective stance. The shrimp's success lies in intercepting a fleeting configuration of exposure. The broader reef ecosystem reflects the consequences of such precision. By preying on shelled invertebrates, mantis shrimps influence the population dynamics of grazers that control algal growth. Reduced grazer density can alter coral algae competition, subtly shifting community composition. Thus, the impact of a single well-timed strike ripples outward, affecting reef structure over time. Yet the mantis shrimp's mastery is confined by its environment. In murky waters where visibility decreases, depth perception becomes less reliable. In turbulent conditions, prey motion becomes erratic, increasing the probability of miscalculation. The shrimp must adapt, relying more heavily on tactile and chemical cues to refine timing. There is a final reversal in understanding the shrimp's weapon. Its power does not derive solely from muscular strength, but from elastic storage and release, a strategy that separates preparation from execution. The strike is the visible culmination of a process that began seconds earlier when the appendage was cocked. The timing decision occurs at the moment of release, but the groundwork for force was laid beforehand. In this way, the mantis shrimp embodies a separation of energy accumulation and energy deployment, a principle mirrored in mechanical systems engineered by humans. As the crab lies fractured, the shrimp drags it toward the burrow, appendage retracting and resetting. The saddle structures absorb residual stress, preventing damage from rebound. The shrimp disappears into shadow, leaving only fragments of shell as evidence. Impact timing precision defines this predator. The mantis shrimp does not rely on repeated blows or extended struggle. It depends on one perfectly timed strike, delivered at the intersection of reach, orientation, and vulnerability. Too early, and energy dissipates uselessly. Too late, and opportunity vanishes. But when timing aligns with geometry, the result is explosive certainty. A demonstration that in the reef's tight margins, survival can hinge on the exact instant when stored force meets exposed weakness. The water detonates into silver panic before a single dolphin reveals itself. Thousands of sardines compress into a living sphere, their lateral lines vibrating with overlapping pressure waves that signal danger from every direction at once. The ball tightens not because the fish are brave, but because geometry has betrayed them. Every escape vector intersects with the accelerating curvature of a dolphin's approach. The predators do not rush the strike. They widen the circle, then narrow it, then widen it again, as if calibrating an invisible clock. Somewhere within that tightening vortex, a decision is forming. Strike too soon, and the sphere fractures into chaos. Strike too late, and the synchronized wall dissolves. Timing is not a detail in this hunt. It is the hunt. Bottlenose dolphins, members of the species Tursiops truncatus, are not merely fast swimmers exploiting speed against slower prey. They are loop builders, architects of feedback cycles in which movement begets compression. Compression begets density, and density unlocks opportunity. Each dolphin emits broadband clicks that ripple outward and rebound from the fish, returning as spatial information processed by a highly folded cerebral cortex. Their echolocation does not simply locate prey, it measures cohesion. As the bait ball contracts, echo intensity changes in texture, revealing how tightly bodies are packed and where microfractures in the formation begin to form. The dolphins are not watching with their eyes alone. They are listening to the density of fear. A solitary dolphin charging into a loose shoal scatters it instantly. Fish evolved to respond to sudden directional threats by exploding outward, maximizing individual survival through chaotic dispersion. Dolphins counter this by imposing circular pressure instead of linear attack. Several individuals swim in arcs around the shoal, exhaling curtains of bubbles that form vertical barriers, while others slice beneath the mass to prevent downward escape. These movements create what biologists describe as a dynamic enclosure, a self-adjusting perimeter whose diameter shrinks gradually. The loop is deliberate. Every pass tightens the geometry by degrees, forcing fish into closer proximity until hydrodynamic escape becomes self-defeating. Within the ball, oxygen becomes limited and collision frequency increases. Sardines rely on synchronized swimming to reduce predation risk, yet extreme density disrupts their coordination. As neighbors brush against one another at unnatural rates, alignment falters. The very mechanism that protects them at moderate density becomes unstable at high compression. Dolphins are exploiting a phase transition in prey behavior, a threshold beyond which collective order collapses into confusion. But that threshold is narrow. If dolphins strike before the bait ball reaches critical density, the fish explode outward and reform elsewhere. If they wait beyond it, the ball fragments under its own instability, slipping through gaps in the perimeter. The window is thin, and the dolphins circle it like engineers watching a pressure gauge. The strike itself is rarely simultaneous. One dolphin lunges into the sphere, jaws agape, capturing several fish in a single snap. Immediately it withdraws, allowing the ball to reconsolidate. This is not hesitation. It is pulse feeding. By entering in staggered bursts, dolphins maintain the sphere's integrity, preventing catastrophic dispersal. The loop continues: compress, test, breach, reset. Each incursion is timed against the ball's resilience. Too many attackers at once would collapse the system. Too few would waste opportunity. The pod behaves less like individual hunters and more like a distributed processor, each member sampling the state of the prey mass and adjusting in response. This coordination is underwritten by neural sophistication. Dolphins possess enlarged temporal lobes and dense spindle neurons associated with social cognition and rapid decision-making. Their brains are adapted not only for communication, but for predictive modeling. As fish density increases, dolphins anticipate how the bait ball will respond to disturbance. They are not reacting in real time alone. They are forecasting seconds ahead, calculating how one lunge will alter the geometry for the next. The hunt becomes a loop of prediction and correction, a living algorithm executed through muscle and sonar. There is a deeper ecological layer unfolding beneath the spectacle. Bait ball events often occur near reef edges or seamounts, where upwelling currents concentrate plankton, drawing small fish into predictable zones. Dolphins learn these locations through cultural transmission within pods. Hunting strategies are not purely instinctual. They are inherited behaviors refined across generations. In some regions, dolphins cooperatively herd fish toward shorelines or shallow sandbanks, using topography as an additional wall. Timing here becomes even more complex. The pod must synchronize the final rush with tidal conditions, current direction, and the fatigue level of the prey. Misjudging any variable alters the loop's outcome. Then the reversal reveals itself. Dolphins are not alone in exploiting the bait ball. Seabirds circle overhead, reading the disturbance from above. Larger predatory fish, tuna, sharks, are drawn by the acoustic chaos and flashing scales. What began as a dolphin-engineered enclosure becomes a multi-species feeding frenzy. The pod's careful timing now intersects with competitors whose arrival shifts the calculus. If dolphins delay too long, sharks may seize the advantage, slicing through the sphere and claiming the densest clusters. If dolphins strike too early, they scatter prey before the density peak that maximizes intake. The predators become both orchestrators and participants in a widening network of opportunists. In this moment, dolphins are not apex controllers, but components in a trophic cascade. Their compression of sardines drives nutrient transfer upward through multiple predator layers. Each successful lunge fuels not only the pod, but also the birds and fish that converge. The hunt's timing reverberates through the food web. A well-executed loop concentrates energy efficiently. A mistimed one dissipates it across the ecosystem. Consider the final tightening. The bait ball has shrunk to a diameter scarcely wider than a small boat. Fish at the core press against one another, scales reflecting in frantic flickers. Dolphins accelerate their arcs, bubbles forming luminous spirals that corral the last gaps. One dolphin emits a rapid burst of clicks, signaling readiness. Another shifts position to seal an opening where the sphere threatens to shear apart. The timing threshold approaches. Oxygen depletion within the ball has slowed the sardine's reflexes. Collision-induced disorientation reduces escape coherence. The system has reached critical compression. Now the strike cascades. Multiple dolphins surge in rapid succession, each bite followed by withdrawal, each withdrawal followed by reconsolidation. The ball contracts further, unable to sustain its structure. Within seconds it unravels entirely, reduced to scattered fragments consumed in swift passes. The loop has closed. But the hunt's success is fragile. Environmental variability can disrupt these timing loops. Increased water turbidity diminishes echolocation clarity, blurring density estimates. Warmer seas alter sardine migration patterns, shifting bait ball formation zones unpredictably. Human fishing vessels sometimes intercept these events, exploiting the same density peak that dolphins have engineered. The pod must adapt, recalibrating loops in an ocean increasingly altered by external pressures. The ultimate revelation is that dolphins do not dominate through raw speed or individual prowess. Their power lies in controlling time within space. They create feedback cycles that shape prey behavior until a narrow moment of vulnerability appears. That moment is not fixed. It is manufactured through coordinated motion. The dolphins are sculpting probability, bending the fluid dynamics of schooling fish toward collapse. As the water settles and silver fragments vanish into open blue, the pod disperses. Their breathing breaks the surface in staggered exhalations, a rhythm echoing the pulses of the hunt itself. Beneath the calm, the memory of the loop lingers, a choreography in which success hinged not on who struck hardest, but on who understood precisely when to strike. In the open ocean, survival often belongs to the fastest or the strongest. Here, it belongs to those who can feel the exact instant when chaos becomes containment and containment becomes opportunity. Dolphins do not simply chase fish. They tune the hunt like a tightening coil, releasing it only when the geometry of fear reaches perfection. Timing does not accompany the attack. It governs it. The fins move like drifting feathers, slow enough to be mistaken for debris, wide enough to look harmless. A juvenile damselfish hovers inches from a coral head, its lateral line attuned to sudden pressure shifts, its retina wired to detect rapid contrast changes that signal predatory acceleration. Nothing in the water around it appears urgent. The striped figure approaching does not surge, does not twitch, does not create the hydrodynamic spike that would trip the fish's escape reflex. The lionfish advances as if time itself has thickened. And in that suspension, when vigilance relaxes just enough, the mouth opens with impossible speed. The strike is over before the prey registers that safety has expired. Lionfish of the genus Pterois do not hunt by chasing. They manipulate perception. In reef systems where small fish survive by reacting within fractions of a second to sudden motion, speed is a liability. The faster a predator moves, the sooner it triggers the prey's Morthner cells, specialized neurons that initiate rapid escape bursts. Lionfish invert this logic. They approach slowly, deliberately, reducing the rate of change in water displacement so that mechanosensory systems fail to classify them as imminent threats. Timing here is not about when to sprint. It is about how long to delay acceleration so that the prey's neural alarm never activates. The lionfish's elongated pectoral fins spread outward like a radial screen, altering the visual outline of its body. To small reef fish accustomed to compact predators with forward-facing profiles, this silhouette reads as ambiguous rather than aggressive. The banded coloration, alternating light and dark stripes, breaks up body contours, interfering with edge detection in the prey's visual field. Each slow pulse of the fins creates minimal turbulence, a hydrodynamic whisper instead of a warning shock. The predator is advancing, but it is doing so below the threshold that would flip the prey's sensory circuitry from calm to flight. The ecological mechanics deepen the strategy. Reef fish operate on a balance between feeding efficiency and predator avoidance. Constant high-alert behavior is metabolically expensive. It reduces time available for foraging and growth. Therefore, prey species rely on predictive cues, rapid approach speed, sudden shadow shifts, sharp lateral movements, to triage which stimuli demand immediate escape. Lionfish exploit this cost-benefit compromise. By moving at a pace that resembles non-threatening drift, they remain categorized as background noise. The prey's nervous system, optimized to avoid false alarms, filters out the lionfish until the final instant. This slow-motion advance is not passive. The lionfish adjusts its trajectory with minute fin flicks, steering prey toward concave reef structures that limit escape vectors. The expanded fins can act as corralling tools, subtly guiding smaller fish away from open water and into tighter pockets. The timing loop here is subtle. Approach slowly, allow prey to acclimate to presence, gently constrain movement, and only when the fish's orientation favors capture does the lionfish accelerate. The strike itself is a burst of precision. Although lionfish glide with deceptive lethargy, they possess rapid buccal expansion mechanics. When the mouth opens, the sudden expansion of the oral cavity generates a suction force that draws water and prey inside. The acceleration occurs at the exact moment when the prey's guard is lowest. If triggered prematurely, the suction would fail as the prey's escape reflex engages. If delayed too long, the fish might drift into a more open position. The lionfish's entire approach is a countdown calibrated against the prey's perception curve. There is an evolutionary irony embedded in this timing. Lionfish are venomous, equipped with dorsal spines that deter larger predators. One might assume that such defenses free them from stealth. Yet venom does not assist in capturing agile prey. The spines protect the hunter from retaliation, but do not replace the need for subtlety. Thus, lionfish combine conspicuous morphology with covert motion. Their dramatic appearance does not function as intimidation for prey. It functions as a shield against would-be attackers. The apparent flamboyance masks a patient assassin. The narrative reversal emerges most starkly in regions where lionfish have become invasive. In their native Indo-Pacific habitats, small fish species have co-evolved with lionfish predation. They recognize the silhouette and adjust behavior accordingly, tightening schooling patterns or avoiding close proximity. In the Atlantic and Caribbean, however, many prey species lack this evolutionary history. They do not interpret the lionfish's outline as dangerous. The slow-motion approach becomes even more lethal because the prey's perceptual model is incomplete. The predator appears ornamental rather than lethal. In these invaded reefs, the timing imbalance has ecosystem-wide consequences. Lionfish densities can increase rapidly due to high reproductive output and lack of natural predators. Their efficient hunting suppresses populations of herbivorous fish that normally graze algae. With fewer grazers, algal growth accelerates, competing with corals for space and light. What begins as a single perfectly timed strike cascades into altered reef composition. The lionfish's mastery of slow-motion timing ripples outward, reshaping trophic relationships. Yet even here, the predator's advantage contains vulnerability. Lionfish rely on the absence of recognition. As native predators such as groupers and sharks begin to incorporate lionfish into their diets in some areas, the balance shifts. Human divers spear lionfish in controlled removal efforts, altering local densities. The once unchallenged slow-motion hunter becomes a visible target. The very boldness of its patterning, once a shield, makes it easier to spot and remove. The strategy that thrives on being misjudged now encounters new forms of assessment. Return to the reef at dusk, when light angles shift and visibility softens. A small wrasser flits among branching corals, its attention divided between feeding and scanning. The lionfish hovers several body lengths away, fins extended, body tilted slightly downward. Each movement is incremental, measured not in dramatic lunges, but in subtle repositioning. The wrasser glances toward the striped form, then resumes feeding. The absence of acceleration reassures it. Slowly, the lionfish edges closer, altering its angle so that escape paths narrow toward a rock face. The wrase's world shrinks, but not abruptly enough to trigger alarm. The predator waits for alignment, prey head angled toward open mouth, fins positioned to block lateral darting. The wrase makes a final adjustment, drifting into the precise pocket where suction will be most effective. In that instant, the lionfish abandons stillness. The mouth opens wide, the body snaps forward, and water surges inward. The wrasse vanishes in a blink, drawn into a vacuum created by rapid expansion. The reef returns to apparent calm, the lionfish resuming its poised hover as if nothing has occurred. The lesson is not that the lionfish is fast. It is that it understands thresholds. It knows that prey react not to presence, but to change. By reducing the rate of change, by dissolving urgency into drift, the predator slips beneath the prey's decision boundary. The strike is timed to coincide with a false sense of equilibrium, a moment when the prey's brain has categorized the striped figure as safe enough to ignore. In the broader choreography of reef life, where color and movement are constant, danger does not always announce itself with speed. Sometimes it advances at a pace so measured that vigilance erodes gradually. Lionfish embody this paradox. Their approach is languid, their fins ornamental, their demeanor serene. Yet beneath that slow unfolding lies a calculation tuned to neural thresholds and escape latencies. Timing here is not about dramatic pursuit. It is about knowing precisely when calm becomes complacency. The lionfish waits for that boundary when the prey's perception of safety is strongest and then collapses it in a fraction of a second. In reefs governed by split-second reactions, survival belongs not only to the swift, but to those who can move slowly enough to remain unseen until the last possible breath of security disappears. The surface shatters in a single silent gasp. A dark, ribboned body breaks through the mirror of the sea, nostrils flaring open for a heartbeat before slipping back beneath the glare. That moment, no longer than the blink of a gull overhead, is the most dangerous act of the sea snake's life. Down below, among coral crevices and sand channels, it is an efficient hunter, armed with venom potent enough to immobilize fish within minutes. But at the surface, lungs exposed and silhouette cast against the sky, it is suddenly fragile. The ocean that conceals it becomes a ceiling of risk. Sea snakes, members of the subfamily Hydrophinae, are fully marine reptiles that breathe air. Unlike fish, they cannot extract dissolved oxygen from water. Their elongated lungs stretch through much of their bodies, functioning not only in respiration but also in buoyancy control. These lungs allow prolonged dives that can last beyond an hour in some species, but such endurance is not infinite. Oxygen stores deplete as metabolism consumes them, and carbon dioxide accumulates in the bloodstream, altering pH and stimulating the urge to breathe. The snake must decide when to ascend. Too early, and it wastes hunting time. Too late, and hypoxia threatens muscular control. The margin between efficiency and suffocation is narrow. Beneath the surface, the sea snake hunts with fluid grace, tongue flicking to sample chemical cues dispersed in the water column. Its body undulates through coral labyrinths, ribs expanding subtly to adjust buoyancy without expending excess energy. Oxygen management here is not passive. Heart rate slows during dives, a phenomenon known as diving bradycardia, conserving oxygen for vital organs. Blood flow is prioritized toward the brain and heart, while peripheral tissues tolerate temporary reduction. Each glide through a reef channel is measured against the ticking chemistry of its own bloodstream. Yet oxygen is only part of the equation. The sea snake must also anticipate external threats. Large predatory fish, including sharks and groupers, patrol reef edges and open water zones. At the surface, seabirds scan for movement, and in coastal regions, human fishing activity introduces nets and boat traffic. Surfacing is not a neutral act. It is a calculated exposure. The snake must rise when the probability of encounter is lowest, often choosing moments between predator passes or in the brief cover of turbid water stirred by currents. The ecological twist begins to unfold in the snake's skin. Sea snakes can absorb a small portion of oxygen, directly through their highly vascularized skin, a supplementary mechanism that extends dive time marginally. This cutaneous respiration does not eliminate the need for air, but it stretches the window between ascents, allowing the snake to delay surfacing until conditions are favorable. What appears to be a vulnerability, air breathing in a marine world, becomes an adaptation fine-tuned by physiology and behavior. Imagine a banded sea crate weaving through a reef slope at dusk. It has already hunted for nearly an hour, venom glands partially depleted from a recent strike on a small eel. Its muscles burn subtly as oxygen levels decline. The urge to ascend intensifies, triggered by rising carbon dioxide concentration sensed by chemoreceptors. But above, silhouettes of Barracuda cut through the upper water column. The snake hesitates, adjusting its path downward into a crevice where water flow is reduced. It waits, conserving energy, minimizing movement to slow oxygen consumption further. This delay is dangerous. If it waits too long, neuromuscular coordination falters, increasing the risk of predation even below. If it ascends now, it may rise directly into the hunting corridor of larger predators. Timing is no longer a matter of convenience. It is a gamble between internal suffocation and external attack. Sea snakes mitigate this risk through route memory and spatial awareness. Individuals often establish home ranges where they learn safe surfacing zones, areas shielded by rock outcrops or shallow lagoons less frequented by large predators. They time ascents with tidal rhythms, using slack water periods when currents are minimal, reducing the energetic cost of vertical travel. The ascent itself is swift, a direct path rather than a meandering climb, minimizing exposure time. At the surface, nostrils equipped with valves open briefly, drawing air into the elongated lung. The inhalation is efficient. The snake does not linger. Its eyes scan for movement above and below, and within seconds it dives again, expelling excess buoyancy by adjusting lung volume and muscular tension. The entire exchange with the atmosphere may last only a few breaths, yet during those breaths, the snake's survival hangs in balance. There is another reversal hidden within this vulnerability. Some sea snakes have evolved to forage in deeper waters, where predator density near the surface is lower, but oxygen management becomes more critical. Their dives are longer, their bradycardia more pronounced. In these species, metabolic rate is finely tuned to conserve oxygen during extended hunts. The risk shifts from surface predation to internal depletion. Timing becomes even more exacting, with ascent thresholds dictated by precise physiological signals. In certain coastal ecosystems, human activity compounds the challenge. Fishing nets suspended near the surface create invisible barriers. A sea snake ascending into such a net may become entangled, unable to reach air. Here, the very instinct to breathe becomes a trap. Mortality rates can rise sharply in regions with intense net fishing, illustrating how evolutionary adaptations can falter under anthropogenic pressures. Yet sea snakes are not merely victims of circumstance. Their venom, among the most potent of marine reptiles, enables rapid subjugation of prey, reducing the time spent in active pursuit and conserving oxygen. Efficient envenomation shortens hunts, allowing longer intervals between risky ascents. Their flattened, paddle-like tails generate powerful thrust with minimal energy expenditure, optimizing locomotion in three-dimensional space. Every anatomical feature intersects with the central constraint, the need to breathe. Consider the moment before the next ascent. The snake has captured a fish and consumed it whole, digestion already beginning as enzymes break down tissue. Oxygen levels are dropping. The surface above glows with refracted sunlight. A shadow passes overhead, perhaps a passing ray, perhaps something more dangerous. The snake angles toward a rocky overhang, aligning itself for a vertical sprint that will place its head within inches of the surface in a sheltered pocket. The ascent is abrupt. Muscles contract in coordinated waves, pushing the body upward. The surface tension parts, and air rushes in. For a second, the snake is half in two worlds, lungs filling, while eyes remain fixed on the shifting patterns below. Then it descends again, folding back into the ocean's concealment. The broader marine ecosystem accommodates this rhythm. Sea snakes influence fish populations through predation, shaping reef community dynamics. Their presence alters prey behavior, which in turn affects algal growth and coral health. yet their impact is modulated by the simple requirement to breathe. Unlike fully aquatic predators, they cannot remain submerged indefinitely. Their predatory pressure is pulsed, dictated by oxygen cycles. In the end, the sea snake's life is governed by a metronome set within its blood. Every dive is a negotiation between metabolic demand and environmental hazard. Surfacing is both salvation and exposure. The ocean offers concealment, prey, and mobility, but it withholds the one element the snake cannot extract from its depths. Breathing, an act so automatic for terrestrial animals, becomes here a perilous decision. Rise too soon, and energy is squandered. Rise too late, and muscles fail. Rise at the wrong moment, and predators seize the opportunity. The sea snake survives by aligning its internal clock with the shifting currents of risk above. In that alignment, between oxygen chemistry and predator patrol patterns, lies the razor-thin margin that keeps it alive in a world where even a single breath can be a gamble. The edge of the ice is a line between worlds, and every penguin standing upon it knows that gravity is not the danger. Beneath the surface, something is waiting. The colony gathers at the lip of the flow, bodies angled forward, flippers half raised, eyes fixed not on the horizon, but on the shifting darkness below. A single leap will convert safety into exposure. One mistimed entry, one misread ripple, and the ocean will close over feathers that never resurface. The hesitation is not fear, it is calculation. For penguins, particularly species such as the Adelie and the Emperor, the sea is both pantry and predator field. Their physiology is engineered for aquatic pursuit. Dense bones reduce buoyancy. Flipper bones are flattened into hydrodynamic blades, and hemoglobin concentrations in their blood permit extended dives into cold, oxygen-poor waters. Yet entry into that realm is the most perilous moment of their day. On land or ice, penguins are relatively safe from marine predators. In the water, they are agile, capable of reaching remarkable speeds through burst propulsion. But the instant of transition, the split second when body leaves ice and meets sea, is a window of vulnerability that cannot be undone. Leopard seals patrol beneath Antarctic ice edges with predatory patience. Their elongated bodies remain almost motionless, whiskers detecting minute vibrations from above. Orcas sometimes cruise along the perimeter of flows, using coordinated wave surges to destabilize ice and flush penguins into open water. The penguins know this. They have learned through evolutionary pressure that entry timing governs survival probability. Jump too early, and a predator may already be positioned beneath. Jump alone, and you become the sole target in an otherwise still landscape. Jump too late, and hunger depletes energy reserves critical for breeding and thermoregulation. At the colony's edge, individuals lean forward and retreat, scanning the water's surface. Their vision, adapted for underwater clarity, is less effective through the refractive distortion of air-water interface. Therefore, they rely on collective vigilance. Multiple heads pivot, each bird sampling the visual field from slightly different angles. The group becomes a distributed detection system, increasing the chance that subtle surface disturbances are noticed. A ripple against the underside of ice, a shadow passing beneath translucent blue, a faint disturbance in current flow. These cues inform timing. The metabolic stakes are severe. Penguins fast while incubating eggs or guarding chicks. When they finally approach the sea to feed, their fat reserves may be significantly reduced. Each delay costs energy, yet each premature leap risks death. The decision to jump is thus governed by a dynamic trade-off between starvation risk and predation risk. Natural selection has tuned their behavior to respond not only to immediate cues, but to contextual ones. Time of day, sea state, known predator activity in recent hours. Often, one penguin becomes the reluctant pioneer. It edges closer, peers downward, and then withdraws. Sometimes another nudges from behind, precipitating an accidental plunge. Yet even this apparent clumsiness carries strategic benefit. If a single penguin enters and survives the first few seconds, others interpret that outcome as provisional safety. Group entry reduces individual probability of capture through what ecologists term the dilution effect. A predator cannot seize all targets simultaneously. By synchronizing entry, penguins convert individual vulnerability into collective advantage. This synchronization requires exquisite timing. If the first penguin jumps and others hesitate too long, the predator can reset its position and target the next entrant. If too many jump before confirming relative safety, they may descend directly into a waiting ambush. The optimal moment is narrow, after a brief observation window suggests absence of immediate threat, but before the predator repositions. Consider the sensory challenge beneath the surface. Leopard seals often approach from below, using the brightness of the sky to silhouette prey against ice. They rely on stealth and explosive acceleration. The penguin's entry must therefore avoid predictable patterns. If individuals always leap at the same interval, predators can anticipate timing. Instead, colonies display irregular hesitation, breaking rhythm in ways that reduce predictability. The ecological twist emerges when examining penguin adaptation to cold. Their feathers trap air for insulation, creating a micro-layer that reduces heat loss in frigid water. Yet this insulating air also increases buoyancy. Upon entry, the penguin must overcome this buoyancy to dive quickly, minimizing time spent near the surface where predators are most effective. Timing the jump to coincide with a powerful downward stroke is critical. If the entry angle is shallow or the stroke delayed, the bird lingers in the predator's strike zone. Emperor penguins, capable of dives exceeding several hundred meters, manage oxygen with remarkable efficiency. Their heart rate drops during dives, and peripheral circulation is restricted to conserve oxygen for essential organs. But none of these physiological marvels matter if the entry itself is fatal. The greatest risk occurs before any of their diving prowess can be deployed. The reversal lies in recognizing that hesitation is strength, not weakness. To an outside observer, the cluster of birds shuffling at the edge appears indecisive. In reality, they are performing risk assessment in real time. Each backward step recalibrates probability. Each collective glance is a vote against premature action. The delay is not fear-driven paralysis, but evolved caution sharpened by generations of predation. When the leap finally comes, it is sudden. A single penguin commits, flippers tucked, body streamlined. The splash is brief. It vanishes below, executing a powerful stroke to clear the surface layer. For a second, the water remains unbroken. Then another penguin follows, then another, until a cascade of bodies arcs into the sea. The synchronized entry overwhelms the predator's ability to isolate a single target. Below, leopard seals may surge, jaws agape, but the confusion of multiple targets complicates pursuit. Penguins accelerate, twisting and darting with agility that belies their waddling gait on land. The moment of greatest risk passes into the domain where their adaptations dominate. Yet the ocean is not static. Climate-driven changes in sea ice distribution alter the geography of entry points. Thinner ice edges may force penguins to jump into deeper, more exposed waters. Shifts in predator distribution can increase encounter rates at traditional entry sites. As the Antarctic environment transforms, the timing calculations that once ensured survival must adapt to new variables. The colony returns at dusk, bellies full, chicks waiting inland. Once again they gather at the ice edge, this time to exit rather than enter. Here, too, timing matters. Surfacing beneath ice must align with gaps or cracks wide enough for ascent. A mistimed rise can result in collision with solid ice, wasting oxygen and increasing predation risk near breathing holes. Penguins exist at a boundary where air meets sea, ice meets fluid, safety meets hazard. Their lives hinge on transitions, moments when one element yields to another. Entry timing is the most dramatic of these thresholds. A fraction of a second determines whether feathers glide through water in pursuit of fish or become a blur within a predator's jaws. In that poised stillness at the ice edge, survival is distilled into a single decision. The penguins do not leap recklessly. They measure currents, shadows, and silence. They read the water as carefully as a diver reads depth gauges. And when the instant aligns, when absence of threat intersects with hunger's urgency, they commit fully, transforming hesitation into motion. The jump is not merely a physical act. It is an ecological negotiation with uncertainty. Each entry is a calculated gamble in a landscape where errors are rarely forgiven. The colony's collective patience, their synchronized plunge, and their rapid descent into the sea reveal a truth of polar survival. Courage is not in leaping first, but in leaping at precisely the right time. The tide is already turning, and the sand is still exposed. A ghost crab stands at the lip of its burrow, antennae lifted into the thinning air, compound eyes raised on stalks that pivot independently to scan both horizon and sky. Behind it, the beach stretches wide and empty, a temporary continent revealed by retreating water. Ahead, the sea is inhaling. Within minutes, channels that are now ankle-deep will deepen into currents strong enough to sweep a small crustacean off its feet. The crab hesitates not because it is slow, but because the clock governing its world is not its own heartbeat. It is the moon's. For crabs that inhabit intertidal zones, ghost crabs, fiddler crabs, mangrove crabs, shore crabs, the tide is not background scenery. It is architecture. Twice each day, the boundary between land and sea migrates across their habitat, redefining where food is available, where predators can reach, and where refuge lies. A mistimed emergence can mean being stranded far from water when avian hunters arrive. A mistimed descent can mean being swept into open surf or trapped in a receding pool as oxygen levels plummet. Their survival depends on synchronizing movement to a celestial rhythm they cannot see but can sense through subtle shifts in pressure, humidity, and substrate moisture. The crab steps out onto damp sand left behind by the outgoing tide. Beneath the surface, microscopic films of organic detritus accumulate as water drains, forming nutrient-rich feeding grounds. For a few narrow hours, the intertidal zone becomes a buffet of stranded invertebrates, algae, and carrion fragments. The crab's chemoreceptors detect faint traces of decomposing tissue, guiding it toward patches where energy density is highest. But this opportunity is transient. As the tide retreats further, the sand dries, increasing evaporative stress. Gills, adapted for aquatic respiration, must remain moist to facilitate gas exchange. Too long away from water, and desiccation impairs oxygen uptake. Thus, the crab feeds within a shrinking window. Its internal circadian rhythms are entrained not only to light cycles, but to tidal periodicity, a phenomenon known as circotidal rhythm. Even in laboratory conditions removed from lunar cues, some crabs continue to display activity peaks aligned with previous tidal schedules. Their nervous systems have internalized the ocean's pulse. Timing errors are not easily forgiven. A crab that lingers too long on exposed sand risks being overtaken by shorebirds whose foraging peaks coincide with low tide. Above, gulls patrol in loose arcs, eyes scanning for movement. To them, the exposed intertidal zone is an open field. The crab's body coloration blends with sand, but motion betrays it. When it moves, it does so in bursts, short rapid dashes followed by stillness, minimizing the duration of visible movement that might trigger a bird's strike reflex. Here again, timing is layered. Move between glances, freeze when shadows pass overhead, retreat to burrow when wing beats intensify. But feeding at low tide is only half the equation. As the tide turns and begins its return, the environment transforms. Channels refill, salinity gradients shift, and aquatic predators move shoreward. Fish that were absent minutes earlier now patrol newly submerged zones, snapping up stranded organisms. If the crab delays its retreat toward higher ground or burrow entrance, incoming water can isolate it in shallow depressions where fish have easy access. The rising tide is not simply water advancing, it is a conveyor belt delivering hunters. The ecological twist lies in how some crabs exploit this same timing to hunt. Mangrove crabs, for example, synchronize activity with high tide to forage among submerged roots where terrestrial predators cannot reach. During these submerged intervals, they climb and feed on algae and detritus while remaining partially hidden. Their movements are coordinated with tidal peaks that offer both access and concealment. Mistiming the tide in this context can mean exposure either to fish below or birds above, depending on water level. Consider a fiddler crab colony on a mudflat. As the tide recedes, Hundreds emerge, males waving enlarged claws in territorial displays, while females sift sediment for organic particles. The surface is briefly alive with motion. Yet beneath this social choreography lies strict adherence to tidal timing. When the first hint of returning water darkens the mud, the colony retreats almost in unison. Burrow entrances serve as vertical escape shafts, allowing crabs to descend below ground where moisture persists even as surface conditions shift. Those that misjudge the timing may find their burrow entrances flooded prematurely, trapping them without oxygen if the tunnel collapses or fills. Intertidal zones are oxygen-variable environments. Pools left behind by receding tides can become hypoxic as microbial decomposition consumes dissolved oxygen. Crabs trapped in such pools must endure declining oxygen concentrations, relying on physiological tolerance and reduced metabolic rates to survive. But prolonged hypoxia impairs locomotion, increasing vulnerability if predators access the pool. Timing departure before oxygen levels drop below critical thresholds is another invisible calculation. The moon's gravitational pull orchestrates this entire system. Spring tides, occurring during full and new moons, produce greater tidal ranges, exposing larger areas of substrate but also flooding higher zones. Crabs must adjust movement patterns accordingly. A burrow safe during neap tides may become submerged during spring tides, forcing relocation. Failure to anticipate these larger fluctuations can result in burrow collapse or drowning. There is a deeper reversal hidden in what appears to be limitation. The intertidal zone, defined by instability, offers protection precisely because many predators cannot tolerate its extremes. Terrestrial predators avoid deep water. Aquatic predators avoid prolonged exposure to air. Crabs, straddling both realms, exploit this boundary. Their ability to tolerate brief desiccation and short immersion allows them to inhabit a niche that oscillates between two predator regimes. What seems like constant risk becomes strategic opportunity when timing is mastered. Yet human-induced changes threaten this delicate synchronization. Coastal development alters tidal flow patterns, reshaping intertidal topography. Artificial lighting disrupts lunar cues that some species use to time reproductive migrations. Climate-driven sea level rise shifts the vertical position of intertidal bands, compressing habitats against seawalls or cliffs. Crabs that evolved to read subtle gradients must now recalibrate in landscapes altered more rapidly than evolutionary time typically permits. As twilight approaches, the tide reaches its highest point. The beach that was broad and sunlit hours earlier is now submerged. A crab that ventured too far during low tide would now be swimming against incoming currents, expending precious energy to avoid being swept offshore. But those that retreated in time remain secure within burrows, moisture maintained, oxygen adequate, predators less able to penetrate. When the tide begins to fall again, the cycle resets. The sand will reappear, the feeding grounds will open, and the crabs will emerge according to a schedule written not in clocks, but in gravitational physics. Each excursion onto exposed terrain is a wager placed against shifting water levels and roaming hunters. Each retreat is a recognition that the environment dictates windows that cannot be ignored. The crab's world is not defined by speed or strength alone. It is defined by alignment with oscillation. To live at the boundary between sea and land is to accept that habitat itself is temporary. The sand beneath its legs will not remain. The water will not stay withdrawn. Success depends on stepping out when resources peak and withdrawing when risk crests. Timing in the intertidal zone is not preference. It is law. The moon pulls the ocean redraws the shoreline, and the crab, small and vigilant, moves in accordance with forces vast enough to shift continents over eons. A single misjudged tide can mean exposure to birds, entrapment in hypoxic pools, or drowning in collapsing burrows. But when timing aligns with the planet's rhythm, the crab thrives in a landscape that appears too unstable for survival. At the edge of each retreating wave, the crab stands once more, sensing pressure, tasting salt in the air, reading the subtle slope of wet sand. It does not rush. It does not linger. It waits for the narrow interval when the sea yields and predators are distant. Then it moves, briefly, precisely, within a window carved by the pull of the moon. The first signal is not visible. It is a pulse of sound that travels through dark water like a tightening fist. Below a trembling cloud of herring, a humpback whale releases a low-frequency call that compresses space into warning. The fish respond instantly, drawing closer together, instinctively forming a defensive shoal. They believe density will save them. They do not yet understand that density is precisely what their hunters require. Far beneath, several massive bodies adjust position in near silence, each movement timed not to collide but to converge. If one whale rises too soon, the circle fractures. If one lags behind, the net collapses. The ocean holds its breath. Humpback whales, Megaptera novae anglia, are among the largest coordinated hunters on Earth. Though individually capable of engulfing thousands of small fish in a single lunge, they often hunt cooperatively in a strategy known as bubble net feeding. This technique depends on mass timing precision across multiple individuals, each whale executing a specific phase in sequence. There is no visible leader, no shouted command. Instead, acoustic cues and learned behavioral choreography align bodies weighing as much as a small bus into a synchronized engine. The process begins below the shoal. One whale dives beneath the fish and initiates a spiral ascent, exhaling a continuous stream of bubbles from its blowholes. These bubbles rise in a widening column, forming a vertical barrier. Fish perceive the bubbles as physical obstacles or potential predators. Their lateral lines detect the turbulence, and their vision interprets the shimmering wall as danger. They tighten into a compressed sphere at the center of the growing ring. Another whale may slap the water's surface with its fluke, adding acoustic shock that further corrals the shoal downward. Each action has timing constraints. The bubble ring must close before the fish find a gap. The acoustic strike must occur when the shoal begins to disperse, not before. As the circle constricts, additional whales position themselves below the trapped fish. They align at depth, often at slightly staggered intervals to avoid collision during ascent. Humpback whales possess expandable throat pleats that allow their mouths to engulf vast volumes of water. Yet this lunge feeding demands precise vertical timing. If a whale accelerates upward before the bubble ring has fully enclosed the shoal, fish escape laterally. If it waits too long, the fish may dive beneath the ring or disperse as the bubble wall weakens. Communication plays a central role. Studies suggest that certain feeding calls, sometimes referred to as feeding cries, are emitted to coordinate ascent. These calls may signal the moment when the bubble net is complete. Acoustic timing substitutes for visual confirmation in the murky depths where sight lines are limited. The whales rely on sound not only to locate prey, but to synchronize with each other. The entire system resembles a living mechanism composed of muscle, lung, and resonance. The ecological twist is revealed in the whale's own anatomy. Their immense size appears cumbersome, yet it enables a hydrodynamic phenomenon known as lunge feeding. As a whale surges upward with mouth agape, it engulfs a mass of water and fish equal to a substantial fraction of its body weight. The pleated throat expands dramatically, increasing oral cavity volume. But this expansion generates drag, slowing the whale rapidly. Therefore, the lunge must occur at the exact moment when prey density is highest. Any miscalculation wastes energy, as the whale expends enormous muscular effort for a mouthful of mostly water. Energy economics shape every movement. Humpbacks migrate thousands of miles between feeding and breeding grounds. During feeding season, they must accumulate enough energy to sustain prolonged fasting while breeding. Each bubble net event must maximize caloric intake relative to expenditure. Coordinated timing ensures that multiple whales share the concentrated prey without diminishing returns. If coordination fails, individuals may collide or deplete the shoal inefficiently. The fish are not passive participants. Herring and similar species are adapted for rapid, synchronized movement. When threatened, they perform flash expansions, sudden outward bursts that disrupt predator targeting. The bubble net counters this by creating a vertical barrier that limits expansion space. Yet the barrier is fragile. Turbulence can disrupt bubble cohesion. Currents can distort the ring. Thus, whales often select specific environmental conditions, calm water, minimal cross-current, to execute bubble net feeding effectively. The timing of tides and local current shifts intersects with their choreography. Imagine the moment of ascent. Beneath the bubble ring, multiple whales accelerate upward in near unison. Their flippers adjust micro-angles to maintain vertical alignment, preventing mid-water collisions. The water above them churns as fish compress into a writhing column. At a predetermined acoustic cue, mouths open wide. The whales breach the surface almost simultaneously, jaws agape, pleats distended, engulfing a cylinder of fish and water that moments earlier was an organized shoal. If one whale were to surge seconds too early, it might rupture the bubble wall before others are in position. Fish would spill outward, reducing prey density and compromising the collective strike. If one whale hesitates, it may rise into a partially depleted zone, capturing fewer fish while disrupting the ascent path of others. The success of the hunt is not additive, it is multiplicative. Each participant's timing influences the efficiency of all. The reversal emerges when considering the origin of this behavior. Bubble net feeding is not universal among humpback populations. It is culturally transmitted. Pods that practice it teach it to younger individuals through repeated exposure and imitation. The complexity of the choreography suggests social learning rather than purely instinctual programming. Thus, the whales are not merely reacting to prey. They are sustaining a tradition of coordinated precision passed across generations. What appears to be brute force is actually cultural engineering. There is also vulnerability in mass coordination. While lunge feeding, whales are temporarily blind and acoustically disoriented, mouths full of water, unable to maneuver quickly. Large predators such as orcas have been known to exploit moments when whales are distracted or calves are present. Timing the ascent in safe contexts, away from predator-rich zones, is essential. The feeding window is not only about prey density, but about minimizing external threat. Environmental change adds further complexity. Warming oceans alter prey distribution, shifting herring schools to different depths or latitudes. Increased boat traffic introduces acoustic interference that can mask coordination calls. Noise pollution disrupts the acoustic timing that underpins bubble net feeding. When communication falters, the choreography unravels. A mistimed lunge in a noisy seascape becomes more likely. Yet when conditions align, the spectacle is breathtaking. The sea erupts as multiple colossal bodies break the surface together, water cascading from open jaws, fish flashing silver against dark pleats. Seabirds dive into the chaos, capitalizing on disoriented prey. The bubble net dissolves, leaving only ripples and fragments. The whales roll onto their sides, expelling excess water through baleen plates that sieve fish inward toward the throat. In that eruption, one sees the culmination of layered timing systems, acoustic signaling, bubble geometry, prey compression, vertical acceleration, and synchronized lunging. Remove any element, and the structure fails. The hunt is not about strength alone. It is about orchestrating a series of events within narrow temporal margins. Humpback whales embody one of the ocean's most intricate timing networks. Their feeding strategy is not solitary ambush or simple pursuit. It is a collective equation solved in fluid dynamics and sound. Each whale contributes a piece of the puzzle: bubble formation, acoustic cue, vertical thrust. The margin for error is thin, yet the payoff is immense. As the ocean settles and the whales descend once more into blue silence, the fish shoal reduced and scattered, the choreography resets. Somewhere below, another cluster of herring flickers in the dim light. Again, the low-frequency call will pulse outward. Again, the spiral of bubbles will rise. And again, if timing is flawless, giants will ascend in perfect unity, turning density into destiny. In the vastness of the sea, where chaos reigns and currents shift without warning, bubble net feeding stands as a testament to precision. It is not merely a hunt. It is a synchronized crescendo in which each participant must move within a shared heartbeat. The entire structure exists for seconds. Yet within those seconds, coordination transforms mass into mastery.